Hello students, welcome to the Champion series, and today we are going to cover the chapter Chemical Kinetics. So my dear students, I hope you all are ready for this amazing session, right? Yes. So how are we going to start this chapter? Why is this chapter important? So let us discuss about this first. In 11th, you have studied about the thermodynamics chapter. It gave you an idea whether a reaction is possible or not, right? Yes. But have you ever thought, if a reaction is spontaneous, how much time will it take to get completed? This is a question mark, and chemical kinetics actually answers this question. So yes, we are going to study about if a reaction is spontaneous, then how, at what rate are the products formed, or at what rate the reactants are consumed. As if we talk about a reaction, it might be spontaneous, it might be possible, but it might take 10 days, it might take an hour, it might take a month, or it might take a year as well, right? So before starting a reaction, you actually need to know what is the rate of the reaction so that you can proceed accordingly. So we are going to discuss about the rate of the reaction in this particular chapter, which is your chemical kinetics. Kinetic words itself refers to something related to rates. So my dear students, let us start this session. So first, in chemical kinetics, we discuss what are we majorly going to discuss, what is motto. What is our motto, right? Yes, so let us discuss about that. The first thing that we are going to study would be rates of the chemical reaction. You know all the reactions. You first find out whether they are spontaneous or not by thermodynamics, and then you discuss about their rate. So first and the first motto is to find the rates of the reaction. What are we going to discuss further? We are going to discuss about the factors that change the rate of a reaction. Obviously, you can alter the rate of a reaction as well. So how can you alter the rate of the reaction? What factors are on what factors are the reactions dependent? We are going to discuss about that. And also applications of kinetics in a reaction mechanism. We will discuss the applications in the organic chemistry, so don't worry, we are not going to discuss the applications here. But yes, we are going to discuss everything about the rate of a reaction, and this chapter is going to be amazing, right? Yes. So let us start. First, rate of a chemical reaction. How do you define a rate? Define the rate of a chemical reaction. You have studied about speed. You have studied about speed in physics. Yes. How do we define speed? Distance traveled by time taken. It is somewhat like that only, speed of a chemical reaction. Now, when you calculate speed of a person, you see that how much distance it has traveled in a particular time, right? Now, if you are measuring the speed of a chemical reaction, what are you going to see? Obviously, you cannot see that how much distance it traveled. No reaction travels a distance. But here, your factor would be how much of your product is formed, right? Yes. Or you can say how much of your reactant has been used, right? Yes, in a particular span of time. So that is how you are going to find out the rate of a chemical reaction. Perfect. So the definition would be, it is the amount of chemical change occurring per unit time. Now, amount of chemical change would refer to change in products amount, or it could be change in reactants amount, right? Yes, perfect. It's very easy. We can find the rate with respect to product as well as with respect to reactant. Reactant will be consumed and product will be formed. Perfect. We only discuss the chemical change in one direction, not reversible reaction. Now, this is a very important thing to always remember in this particular chapter. All the reactions which we are going to discuss would be in a single direction. The concept of that equilibrium, that every reaction is at both sides, is taking place at both sides, we are not going to discuss about that. We will take this assumption that every reaction is a single direction reaction. Okay? Yes, only then you can study chemical kinetics. Perfect. Next, the amount of chemical change can be measured. Now, how much amount of chemical change? How can you measure it? It can be measured in terms of decrease in the concentration of reactant reactant. If it is a reactant, you have to find the decrease in concentration of reactant or increase in the concentration of products. Right, now let's study about this. How are we going to talk about it? Okay, yes, we know that whenever we talk about a reaction, reactant gives you products, right? Initially, you have a whole lot of reactants, but you don't have any product, right? At time 0, when the reaction has not started, you'll have reactant enough, but you will not have products. After some time, let us say you have, let's say, A moles and you don't have any product at T is equal to 0. Now, at some T time, what will happen? You will have, let us say, some A minus X reactant left. Let us say X amount of reactant has been consumed. Then how much of your product would have been formed? Ma'am, X amount, X moles would have been formed. Right? Yes. So, my dear students, now you can find the rate of the reaction. What is the time taken? What is the time taken? Ma'am, time taken is, you took T time from 0. So, you could say, ma'am, T minus 0, which is equal to T seconds. Let us say you took T seconds of the time. Okay. Now, how much of your reactant is consumed? Because initially it was A and then some amount was left. Yes. So, how much of your reactant is consumed? Let us talk about that. Rate, reactant consumed. Okay. Ma'am, this would be X moles, because initially it was A and now A minus X is left. So, how much is used? X. Perfect. So, ma'am, X amount of reactant is consumed. Similarly, when you talk about the product formed, how much of your product is formed? Ma'am, initially it was 0. There was nothing as such for a product, and after that X moles of product was formed. So, ma'am, X moles of products are formed, right? Yes, perfect, my dear students. Now you have to find the rate. How are you going to find the rate? Rate with respect to the reactant. Rate with respect to the reactant. My dear students, rate is always a positive quantity, right? So what do? You always take mod. You always take mod. Okay, yes. So if I am calculating the rate with respect to reactants, so I would say how many moles of reactant has been consumed. How many? X moles divided by T, total time taken. Similarly, if I talk about the rate with respect to the products formed, how many moles of products are formed? Ma'am, again, X moles. And how much time is taken? T. And this should be in mod, because rate will always be a positive quantity. Okay. So, yeah, ma'am, we got this, that we can find the rate. We can find the rate as concentration of reactant consumed divided by total time taken. Or you could say that this is equal to the products formed divided by the time taken. Right? Yes. Perfect. Now, this is in very layman language, but now you have to go through the signs as well, right? Yes. So here I am going to tell you something very, very interesting, which is that whenever you talk about reactants, my dear students, since the reactants are getting consumed, so you always calculate their rate. You always calculate their rate with a minus sign. And what does this negative sign represent? That your reactant is getting consumed. So minus concentration of reactant, used divided by the time taken. Okay, and the same rate for the same reaction would be equal to plus of concentration of product formed divided by the time taken. So here, if you don't want to take the that mod sign, then you can specify your rate as with the negative sign. If there is a negative sign, everyone will understand that this is the concentration of a reactant, and this negative sign actually indicates that reactant is consumed. Okay. And this positive sign actually denotes that product is formed, and that is the reason you are giving it a positive sign. So here you would say product is formed. Perfect. No issues, right? So this is the first way of defining rate. Right now, we are going to define rate in n number of ways, but this is the first way, right? And I hope it is very interesting and it is very easy, right? Perfect. Now let's move forward. Now, when I am talking about rate, I just want to tell you that rate can be of two different types. Like you talked about speed in physics, you used to say that speed can be calculated in two different ways. It can be, ma'am, average speed, and it can be instantaneous speed. The speed at some instant would be your instantaneous speed. The speed that you calculate, that you see while you are driving in the speedometer, what is that? That is the speed at that particular instant. Yes, ma'am. So that is your instantaneous speed. Speed at some instant. The same way, rate at some particular instant would be your instantaneous rate. And if you talk about the average rate, then what would be average rate? Ma'am, how much of the concentration has changed over a long duration of time? Over a long duration of time would give you an average rate. That would not give you an instant rate, right? Instant rate would be at very particular, very at a specific time. Right? Yes. But if you talk about average rate, then that would be at some long duration of time. Right? Yes. So now we are going to discuss about the two different types of rates. Okay. So let's say that, ma'am, rate can be of two types. First can be instantaneous rate, and the other would be average rate. So you can define them as well. Rate at some particular instant, right? Yes. So we would say that rate at a particular instant / time. Or you could say for average rate is the rate of a reaction over a long duration of time. Over a long duration of time. Perfect. Now what are we going to do? We are going to plot a graph. We are going to plot a graph between rate and time, and then we are going to differentiate between these two types of rates. Okay. Yeah. So here is the graph. Here we are going to talk about rate, and here we are going to talk about time. Okay. I'll try to give you a straight line. Is it straight? Yes, ma'am. Nearly straight. Perfect. Now, my dear students, imagine the rate. Okay. You have to imagine the rate. This is your rate. With time, your rate is decreasing. Okay. This you have to understand. Now, if I ask you to calculate the rate, average rate, okay, if I am asking you to calculate the average rate from T1 time to T2 time, okay, you have to calculate the rate from T1 time to T2 time. Let's say that this is your T1 time and this is your T2 time. How are you going to wait. This would be concentration. Yeah, this would be concentration of reactant. Then you will calculate concentration of reactant. Let's say this is concentration of reactant. Then you will understand, not rate. Yeah, rate will also decrease with time, but here we are talking about the concentration. Obviously, initially reactant's concentration is highest, and with the time it keeps on decreasing. Right? Yeah. Now, if you're supposed to calculate an average rate between T1 to T2 time, then you need the change in concentration of the reactant to the total time taken. Yes. What would be the total time taken? Ma'am, T2 minus T1. This is your T2 time from 0 to T2, and T1 time this is, so you will calculate the total time as T2 minus T1. So first is total time taken. This would be, ma'am, T2 minus T1. Okay, this is basic physics which you have already discussed, studied. Perfect. Now you can find out the concentration of reactant at this T2 concentration. Let us say this is A2. Okay, at T1 time, the concentration of your reactant would be, let's say, A1, right? Yes, ma'am. So what is the change in concentration? Initially, it was A1 and then you had A2 concentration, right? T1 temperature, you had A1 concentration and then you were left with A2 concentration. If you want to find out that how much it is left, you would say that, ma'am, concentration of reactant would be A2 minus A1. Can I say this? A2 minus A1, final minus initial concentration? Yes. Time taken, you have calculated. Can you find the average rate? Yes, ma'am. So, my dear students, average rate would be equal to change in concentration. Since it is a reactant, ma'am, negative sign will be there if we are not taking mod. If you are taking mod, then everything is normal. So, ma'am, negative sign. Right, now see, A2. My dear students, A2 is less than A1. So, A2 minus A1 will be a negative quantity. Now, negative into negative will give you a positive value. Yes. So, this is the reason you put this negative sign, right? Also, this indicates that this is the rate with respect to the change in reactant. Perfect. So, you could say that A2 minus A1 upon total time taken, which is T2 minus T1, and T2 minus T1 is a positive quantity. Perfect. So, this is how you calculate the average rate. Perfect, ma'am, at a long duration of time. Now, if I ask you, I have changed the question. Now, I am asking you to calculate the instantaneous rate. You have to calculate the instantaneous rate at some time T dash, because instantaneous rate would be at some particular instant. Yes. So, if I ask you to calculate at some particular time T dash, then let's say this is T dash. So, how are you going to calculate the instantaneous rate? You have to plot a tangent here. Yeah, ma'am. And this particular point will give you your instantaneous rate. And when you draw a tangent, now let's move to your maths. When you want to see the slope of your tangent, how do you calculate the slope of the tangent? That instant, the partial change, that the small change that has been there in the reactant to the that particular change in temperature, change in time, right? Yes. So, how do you calculate it? You could say that this would be equal to minus dA, the concentration change of reactant. So, I have put the negative sign as well, and dt, right? Yes, this would give you that the change at that particular instant. So, from here we can say that instantaneous change would be equal to minus of dA by dt. So, this is the basic difference between instantaneous rate and average rate. You are asked to calculate the average rate as well, and sometimes you are asked to calculate the instantaneous rate as well. Okay, yes. So, ma'am, we are clear with the rate questions. Perfect. Very good. Let's move forward. Since rate itself changes with time, it is better to go for instantaneous rate. So, whenever you talk about the changes, if you are not asked, it's better to always talk about the instantaneous rate, right? Because it gives you a more precise picture. Perfect. Let's move forward. Now, the other thing which is most important would be, now, ma'am, we have talked about rate. Yes, no issues. First of all, yes, my dear students, we have to talk about the units of rate. Units of rate, yes, ma'am. So, units of rate, and then we'll move forward. Now, if you talk about units of rate, how are you going to talk about the unit? Okay, ma'am, rate is equal to some concentration change divided by the time taken. Yes. If you talk about concentration, the concentration would always be in molarity. The concentration terms we discussed, yes. The concentration would be always in molarity, be it reactants, be it products, it doesn't matter. Concentration would be in molarity. This means that if we talk about the units, then, ma'am, concentrations unit would be molarities unit, which is number of moles per liter. That means mole per liter divided by, my dear students, time taken, which is T. So, times unit is second. So, if you are asked about the units of R, that is your rate, would be mole per liter per second. Mole per liter per second. This is very important. You will be asked questions related to this as well. So, this is how you will give the unit of rate. Clear? Yes. Very good. Perfect. Let's move forward. Now we are going to talk about the factors that actually affect the rate. Okay, see, initially you have a whole lot of reactants. Then the reaction would be fast. Yes, ma'am, obviously it would be fast. Slowly and slowly your reactant would keep on decreasing. It is getting consumed and your products are getting formed. So slowly and slowly we could say that the rate would eventually keep on decreasing because the concentration is decreasing. Right? Yes. It's just like you are sitting in a room where you had a whole lot of cake and you were very hungry. You just started eating it at a very high rate. Now, at a particular time, your cake's amount just got reduced. Now, what will happen? Now, you will see that, okay, now my amount is less, so I'll eat slowly and slowly so that it will not get finished. Right? Yes. So, we could relate it like that. The rate actually depends on the reactant's concentrations. Okay, yes. So what are the factors? First factor is concentration of the reactant. Concentration of the reactants. The other factor would be your temperature. The other factor that it depends would be on temperature. How is it related to temperature? Imagine a reaction is just taking place, right? I'll also give you the technical reason also, but right now you can just understand it that initially the reactants had some energy and they were reacting and they were very happy. Okay, you increased the temperature. The time you increase the temperature, reactants had more of the energy. They'll react even more. Yes, I'll tell you how it depends technically, but right now we can say that yes, ma'am, temperature is a dependent factor for the rate of a reaction. Yes. So second factor would be temperature, and we are going to discuss this in Arrhenius equation. Okay, this is a topic which we will discuss in this one short session at the end. Next would be nature of reaction. Obviously, what is the nature of your reaction? That actually matters. If your reactants are solid or liquid or gas, the rate would differ accordingly, right? Yes. Next is your catalyst. Whether you are using a catalyst or not, your rate actually depends on the catalyst as well. So we are going to discuss each and every factor individually, but first we need to know what are the factors on which the rate depends. So these are the 4 factors on which the rate depends. Okay, perfect. Now let's move forward. Now, I have given you a reaction. Effect of concentration on rate. Okay, you have a particular reaction which is 2A plus 3B gives you C plus 4D. Right now we have found out that how are we going to define the rate, instantaneous rate, right? So how do you define the instantaneous rate? Here we are going to talk about that. Now my dear students, you can calculate the rate with respect to the reactants as well as products. Yes, and you can even calculate the rate with only one reactant, only one product. Anything, any reactant, any product, be it any reactant or product, if they are from the same reaction, it will give you the same rate. This means that if I calculate the rate with respect to A or with respect to B or with respect to C or with respect to D, all the rates would be equal. So what is the expression for expressing their rates? Now we are going to study about that. Okay, perfect. So we know that rate is equal to, now let's talk about reactant A. Since A is a reactant, ma'am, I know that rate is calculated as change in the concentration of the reactant divided by the time taken. So dA by dt is perfect. So I can write dA, change in concentration of A by dt, because we are writing the instantaneous rates. Since it is a reactant, ma'am, we will put a negative sign. Okay, we will put a negative sign because reactant gets consumed. Next, my dear students, you have to see the stoichiometric coefficients. These are the stoichiometric coefficients. Now, whatever the stoichiometric coefficient is, just divide the rate by that. Okay, this is a factor which you have to remember, that whenever you are given the stoichiometric coefficients in a balanced chemical reaction and you are supposed to write the rate expression, always see whether it is a reactant or product. Accordingly write the instantaneous rate, accordingly put the sign and divide the rate by their stoichiometric coefficient. So if I see 2, then the stoichiometric coefficient would be divided, which is minus 1 by 2 dA by dt would be the rate with respect to A. Now I know that I have to calculate the rate with respect to B as well. Yes, ma'am. B is also a reactant. Yes. So we will write dB by dt. Since it is a reactant, you will put a negative sign, and ma'am, it has a stoichiometric coefficient 3. So this would be 1 upon 3. This is the rate of the same chemical reaction at the same temperature. Here, my dear students, you are taking temperature to be constant, okay? Now, it is the rate of the same reaction at the same temperature. Then what will happen? Obviously, this rate and this rate should be equal. So, my dear students, these both rates will be equal. Now you are supposed to find the rate of the same reaction at the same temperature for the product C. So for C you would say, ma'am, change in concentration of C by dt. Now since C is a product, so we will put a positive sign. And it has a stoichiometric coefficient 1, so 1 upon 1 is 1, so it is equal. So ma'am, and this rate would be equal. Yes, this rate will be equal. Perfect. Let's move forward. Next is, ma'am, D. With respect to D, again, change in concentration by time. D of D by dt. Positive sign, stoichiometric coefficient 1 upon 4. My dear students, you calculate with any one factor, you will get exactly the same rate. Right? This is how you express the instantaneous rates for a particular chemical reaction. Okay, perfect. Very good. If you have understood this, then you are going to read the next points. Okay, so now let's read the points. The rate constant, okay, rate constant we will discuss. Right now we have to discuss about the rate law. Okay, now I have given you an expression to calculate the instantaneous rates with respect to reactants as well as products. Now we are going to talk about the rate law. What is rate law? Rate law actually shows you that how your rate actually depends on the concentration of reactants. Okay, so rate law, it gives the expression of how rate depends on the concentration of reactants. Okay, perfect. We know that the more the concentration of reactant, the more your rate, the more the concentration of reactant, the more would be the rate. Eventually, when the reactant's concentration keeps on decreasing, the rate also decreases. So, I can say that the rate is directly proportional to, let us assume a reaction and then we'll talk about it. Now, let's say I have a reaction from A to Na. Okay, this is my reaction, which is reactant is A and my product is NB. So I know that the rate would be directly proportional. Okay, first I'll give you, I'll make you understand this with a simple reaction and then we'll write the general formula. Okay, if I give you a reaction, let us say you have 2A which gives you B. Okay, this is a particular reaction. You have to find the rate. You know that rate would be directly proportional to the concentration of the reactant. Okay, yes. Now, my dear students, you just have to remember this thing, that when you find the rate law, here A to the power X is written. Where what is X? X is order of the reaction. Order of reaction. And the most important thing, that X can be equal to 2 or not. Now, what does this mean? We didn't understood this. Now I am going to make you understand this concept. Okay, when you talk about rate, you know that rate is directly proportional to the concentration of the reactant. Rate law says that rate of a chemical reaction is directly proportional to the mass action of a reactant raised to the power their stoichiometric coefficient. So we always talk, whenever we talk about mass action, we only take the concentration because there is a factor of activity which we generally ignore. Okay, so we generally take concentration here, and here is the order of the reaction. Now, my dear students, this X value can be equal to the stoichiometric coefficient or it might not be equal to the stoichiometric coefficient. Why? Now we are going to discuss about that. If you have a single step reaction, then your order, that is X, will be exactly equal to 2. If I say that 2A to B is a single step reaction, then X will be equal to 2. But If it is not a single step reaction, if it has a lot of mechanism, right, like the reactions you might have studied in organic where you were given a particular reaction but it had a particular mechanism, right? Yes, then in mechanism you see there are 100 lots of other products which are formed which are not actually shown in this reaction. So that type of reactions are your complex reactions, and in that type of reactions, my dear students, X is not exactly equal to the stoichiometric coefficient. Why? Because it is a complex reaction and X will have some other value. So what we say that rate law actually gives you the expression of how the rate depends on the concentration of the reactant, where X is the order of the reaction, but it is a experimental quantity. It is a experimental quantity and it might or might not be equal to the stoichiometric coefficient. You will be given in the question what is the rate of a particular complex reaction. Okay, yes, so I can say that X is experimental. X is experimental. Okay, yes, you'll understand this slowly and slowly. Now we will write a general reaction. Now if I'll write a general reaction, you'll understand it. Imagine you have a general reaction Na2B. Okay, now you know that according to the rate law, R will be directly proportional to the A to the power N, where N can be or not equal to the stoichiometric coefficient. Okay, it might or might not be equal to the stoichiometric coefficient. Perfect. Now, whenever you remove this proportionality, you get R is equal to Ka power N. Okay, this is your expression for rate law. And what does this K stand for? Here, my dear student, this K is your rate constant. This is a rate constant and this is a constant value. This is a rate constant and it is a constant value. Okay, it does not depend on the concentration of reactant or anything. K only and only depends on the nature of your reaction and the temperature of your reaction. It is very important. Now we are going to write that K depends on only two factors. First is nature of the reaction. And second is your temperature of the reaction. As long as the temperature is same, you change the concentration, temperature of reaction, you change the concentration of reactants, K value will not depend on that. Okay, yes ma'am, perfect. I hope you are clear with this concept. What we did, we just found the rate law. Yes ma'am, we found the rate law where the N value, which is the order of the reaction, it might or might not be equal. You can write it like this. N is the order of reaction. Order of reaction. It might or might not. Okay, I'll just improve the English. It might or might not be equal to the stoichiometric coefficient, right? If it is a single step reaction, then it will be equal to the stoichiometric coefficient, and if it is a complex reaction, then it will not be equal to the stoichiometric coefficient. Perfect. When you write the rate law, it is A directly proportional to R directly proportional to A power N, where N is the order of the reaction. When we remove the proportionality, we get a proportionality constant, and that constant is known as the rate constant. And what are the factors on which K depends? That is, your rate constant depends only on two factors: nature of the reaction and the temperature of the reaction. As long as the temperature is constant for a particular reaction, there will be no change in K value. Now, the next point comes units of K. This is very, very important. You are asked a whole lot of a question from this particular point. Okay, how are you going to calculate the unit of K? That is your rate constant. Okay, now we know that R is equal to K A power N, where N is the order of the reaction. So ma'am, K will be equal to rate upon A power N. Yes. Now my dear students, do you know the rate units of rate. We just calculated the units of rate. Yes, ma'am, which is mole per liter per second. Perfect. Yes. Below is the concentration raised to the power n. So unit of concentration would always be molarity is unit, mole liter inverse. Yes, ma'am. Whole to the power n. Perfect. So we can write it as mole per liter per second divided by mole power n liter inverse n. Perfect. Now take this to the numerator. You will get units of K, which will be equal to mole 1 minus n liter n minus 1 second inverse. And this is a very, very important expression for you, because you are asked a lot of questions from this. You actually are given a particular value, or you are given units of rate constant, and you are asked that which order reaction is this, which order's rate constant is given. So you have to see the units and you have to calculate. I'll give you an example as well. Okay, now let us say you have a zero order reaction. You have a zero order reaction. Zero order reaction means that your n value is 0. Your n value is 0. It will be a zero order reaction. So rate would be K A power 0, right? Yes. So my dear student, units of K would be mole 1 minus n liter n minus 1 second inverse. This would be mole liter inverse second inverse, right? Yes. So the question would be, you have the rate constant equal to 0.229 mole liter inverse second inverse. Give the order of the reaction. You have to give the order of the reaction. It would be, you just see the units of rate constant and you could say that, ma'am, this is a zero order reaction. Now other question you are going to solve. Pause the video and just do it. You have to calculate for, this is first, this is second, you have to calculate for first order reaction. Okay, now you are supposed to calculate for first order reaction. Just follow the steps we just did. For first order reaction, ma'am, n will be equal to 1, right? Yes. So rate would be K A power 1, since your order is 1. Perfect. Now my dear students, units of K would be mole 1 minus n liter n minus 1 second inverse. This would be mole this would be something x raised to the power 0 would be 1, liter raised to the power 0 would be 1. So ma'am, the unit would be second inverse. Okay, now whenever the rate constant's unit is in second inverse, just just understand that it is a first order reaction. So this is how you are going to write the first order reactions. Okay, so pause the video and you can write all these. Okay, so now we can start again. Now we are going to read some points and we are going to revise what all we have just discussed. Okay, the rate constant K does not depend on the concentration. It does not depend on the concentration of reactants. It only and only depends on the nature of the reactants. But it depends on the nature of the reaction. It depends on the nature of the reaction and the temperature. Okay, these are the two factors on which it depends. Rate law is experimentally verified. Again, my dear students, rate law is experimentally verified. Why? Because you use order in that particular point, and order is an experimental quantity. So it is experimentally verified and it may not correspond to the stoichiometric coefficient. In all the cases, it might not be equal to the stoichiometric coefficient. Right? Perfect. Let's move forward. Next is, it is order of a reaction. Yes. Now we are going to discuss about order of the reaction in detail. Yes. Yes. First and the most important thing that I know is, order of a reaction is actually an experimental quantity. It depends on the mechanism of the reaction. It does not depend on only that one reaction that we are given. It is, if it is a complex reaction, if it has a mechanism, then order is dependent on that mechanism. It is an experimental quantity. We cannot just give the order like this. It cannot be equal to the stoichiometric coefficient. It is the number of concentration terms involved in the rate of the equation. Okay? Okay, perfect. Now let's move forward. If we talk about order, we can say that, you can write the other point, or we have, it is written. No. Okay, now you have to write, it is an experimental quantity. It is an experimental quantity. If it is a complex reaction, if it is a complex reaction means a reaction which has a proper mechanism. Okay, if it is a complex reaction, order might not be equal to the stoichiometric coefficients. Clear? Perfect. No issues? Yes. Next, my dear students, the other point would be order. Since it is an experimental quantity, it is not necessary that it will have a value 1, 2, 3, 4. It can have a fraction value as well. It can be equal to 1.2. It can be equal to 2.5. It can be equal to 3.2. Right? Yes, it can be a fraction. It can also be a negative value as well. It can be -2. It can be -3 as well. Right? Yes. So, the most important point would be order can be positive value, positive, negative, or a fraction. Okay, so order can have any value. It can have any value. Perfect. So these are the major points about order of a reaction. Perfect. You can pause the video and write these points, and now we are going to move forward. Next. Now, this is the type of questions that you are generally asked to calculate the order of a reaction. How will you calculate the order of a reaction? You will be given like these for a particular reaction which is A plus B, let's say, gives you some product. For this particular reaction, you are given 3 different rates at different concentrations of your reactant, and you are asked to calculate the order of the reaction. So how are we going to solve these type of questions is the major part. We know that rate law. Yes, ma'am. According to rate law, we can say that R is directly proportional to A to the power A and B to the power B, where A is the order with respect to A, and B is the order with respect to B. Right? Yes. Perfect. Now we are going to remove the proportionality. We will get R is equal to K, A power A and B power B. Now, my dear students, the information you have been given, you are supposed to use that. How are you going to use that? See the first reaction. If you see the first reaction, you are supposed to write the equation here. That rate law you are supposed to write. Now here, what is the value of rate? I know that R is equal to K, A power A and B power B, right? Yes. Now, my dear students, what is the rate? Ma'am, it is 0.1. So, my dear students, I can say that 0.1 will be equal to concentration of A, which is 0.01 raised to the power A. Concentration of B, 0.01 raised to the power B. Yes, ma'am. Here, this would be your first reaction. Okay. Second reaction, rate. What is the value of rate? 0.2. This will be equal to 0.2 will be equal to concentration of A, 0.02 raised to the power A and 0 concentration of B raised to the power B. This will be your second reaction. Now equation, let's talk about the third. Rate is 0.4 and this would be equal to 0.01 raised to the power A and 0.02 raised to the power B, right? This will be your third equation. Now, what are you going to do? That is the main part. Always remember, whenever you are given these type of equations, you write the equations and you are supposed to cancel out some one concentration, right? So, if I see first, second and third equations, I can see that in first and second, concentration of B is exactly same. So, if I divide 2 by 1. If I divide 2 by 1, then this will be cancelled out. So your one coefficient will be cancelled out. Then you will have to find the value of the only one coefficient. You have one equation, you have one coefficient, you can calculate its value. Right? Yes. So I will be dividing second equation by first. If we divide the second equation by first, what are we given? 0.2 is equal to 0.2 raised to the power A, 0.1 raised to the power B. 0.1 or 0.02? Okay, it is 0.02. Okay. 0.02 raised to the power A and 0.01 raised to the power B. This will be 0.1 divided by 0.01 raised to the power A and 0.01 raised to the power B. Divide these two equations. Now you can see you can cancel these two. Yes, ma'am. So 2 by 1 will give you 2 by 1 value. This will be 0.02 by 0.01 raised to the power A. Right? This means that 2 is equal to 2 raised to the power A. So what is the value of A? Ma'am, A will be equal to 1. So order with respect to A will be equal to 1. Okay, yes. So you found out the order with respect to one particular reactant. Now let's find for the other. Now for the second, if you want to calculate the value of B, then you have to cancel out A. Yes. So find out the two reactions where you can cancel out A. Here is 0.1 and 0.1. Yes, ma'am. So we can divide third equation by second. Okay. So, third equation by first. So let's divide third equation by first. Yes. What will be 0.4 divided by 0.1, 0.01, 0.02. Okay, so 0.4 would be equal to 0.01 raised to the power A, 0.02 raised to the power B. This will be 0.1 is equal to 0.01 raised to the power A and 0.01 raised to the power B. You're supposed to divide the two. Yes, ma'am. This will get cancelled out. So 4 by 1 would be equal to, I can say 2 by 1 raised to the power B, my dear students. So 4 is equal to 2 raised to the power B, and I can say that 4 can also be written as 2 square 2B. So B value would be 2. So order with respect to B is 2, right? Yes. So what can we say? We can say that order with respect to A is 1 and order with respect to B will be 2. And the third thing is overall order. Overall order would be 2 plus 1, which is equal to 3. So overall order of your reaction would be 3, right? So these type of questions are very common in your exams and you are supposed to do these questions in like seconds. Okay, so this is the first time we were doing, so I took a lot of time, but you have to calculate it very fast. So you need a lot of practice, right? Perfect. So the overall order would be 3, order with respect to 1, A and B you have calculated. Perfect. Let's move forward. Okay, chemical kinetics. Therefore, order is an experimental quantity and it may not correspond to the stoichiometric coefficients of the reactants. Clear? No issues? Perfect. Let's move forward. Now, my dear students, we are going to talk about different types of reactions. Since I said that order is the experimental quantity and for a unitary method reaction it will have different value and for complex reaction it would have different value. So here what it is, we are going to talk about the different type of reactions. You have one step reaction or you might have a multi-step reaction. Okay, so yes, you can write this and then we'll move forward. So now if we talk about one step reaction and multi-step reactions, what can we say? We can say that one step reaction means that it took place only in a single step. Yes, ma'am. You had a reactant, it just gave you a product, right? Yes. If you talk about multi-step reactions, this means that if you are supposed to convert A to D, then this will not take place in a single step. What will happen? Let's say A would get converted into B and then B would be converted into C and finally C would be converted into D. So these three reactions are the mechanism of the particular reaction above, right? Yes. These type of reactions are known as complex reactions. Okay, my dear students? Yes. So what I want to tell you is that For such complex type of reactions, you can only define its order, and that order would be experimental. But when you talk about single step reactions, then whatever the stoichiometric coefficient of your reactant is, that is exactly equal to your order, right? Yes, but for that, whatever the stoichiometric coefficient is of A, that might or might not be equal to the order. Okay, now let's discuss further. Okay. Yes. Now, how do we differentiate between a single step reaction and a multi-step reaction? Imagine you have a energy profile diagram. Whenever you talk about a energy profile diagram, what does this mean? Now, if your A is getting converted into B, what will happen? You will have some reactant. Let's say this is its energy profile. Energy is increasing here. So reactant's energy would be more only because energy of reactant is more. It will be converted into product whose energy would be less. So let's say that here is your product whose energy is less. Always I told you that the more stable a compound is, the lesser would be its energy. So product is more stable, reactant is comparatively unstable, so reactant wants to get converted to products. How this reaction actually takes place is you get something like this. That is, your reactant first goes up somewhere here, you get a transition state here. This state is known as a transition state, and eventually you move forward to the product. Okay, yes, this is the basic idea. We'll talk about this in detail in the further session. Now, my dear students, this is some particular amount of energy, minimum energy, which a reactant should have, only then the reaction will take place. Okay, yes, since there is only one transition state, this is a single step reaction, or you can say that this is a elementary reaction. Elementary reaction means, ma'am, it is a single step reaction. Okay, perfect, no issues. Yes, ma'am, whenever a reaction has only one transition state, it is a single step reaction. If a reaction has multiple transition states, for example, you have a reaction something like this. Here is your energy profile. Let's say this is your reactant and this is your final product. Okay, first let's say your reactant gets converted to some one product, then there would be something like this, and eventually it reaches here. Just a second, huh? Something like this, and eventually it just reaches here. So here what you can see, that you have multiple transition states. This is your transition state 1, this is your transition state 2, and this is your transition state 3. So my dear students, this is a multi-step reaction. Okay, perfect. So now we can differentiate between a single step reaction and a multi-step reaction. A reaction which has one transition state is a elementary reaction, one step reaction. A reaction which has multiple transition states, it will be a multi-step reaction. And multi-step reactions are complex reactions. You can only define its order experimentally, but if you have a one-step reaction, you can see its order that will be equal to the stoichiometric coefficient of the reactant, right? Yes. Now you can read this. Transition state, the state when the bond fission and the bond formation are simultaneous. What is this transition state? I want to make you understand this. Let's say A2 plus B2 wanted to change into AB. Now, if A2 and B2 wants to be changed into AB, what will happen? Obviously, AA bond will break. What will happen, ma'am? AA bond will break, BB bond will break, and what will happen simultaneously? AB bonds will be formed, right? This is what takes place in this transition state. Bond breaking of the reactants and bond making of the products is what is going on in the transition state, and it is very unstable. Once these bonds are formed, you just reach to your product side. Right? Yes. So this is what is defined here, that the transition state when the bond fission and the bond formation takes place simultaneously. A reaction in which there is only one transition state is known as an elementary process or a one-step process. Now, the other factor which we are going to discuss is molecularity. What is molecularity? Now we are going to talk about molecularity. Okay. Actually, my dear students, molecularity tells you that how many reactants actually were taking place in a particular reaction. Most important thing about molecularity is it is only and only defined for elementary reactions. Molecularity cannot be defined for complex reactions. So you can write this point that only defined for elementary reaction. Okay, because what does elementary reaction, what does molecularity tell you? That how many reactants were actually taking part. Let's say you had AA reactants. Now, when AA reactants would collide, you will get some B product. Let's say you will get some B product. So, how many reactants were taking part? Ma'am, 2 reactants. So, the molecularity would be 2. If you had only one reactant and something happened and you got a B products, then you would say that molecularity is equal to 1, right? Now, if you have 3 reactants and you get some B product, what will happen? Here, ma'am, the molecularity would be 3. But the most important thing is that all the reactants should be in touch with each other, right? Yes. So, till 3, we can suppose that yes, all the reactants could touch each other. Here they can touch each other. But my dear students, if I had 4 reactants, now if I had 4 reactants, let's say here, here, here and here, A. If I want them to collide, what will happen? A and A. Can you see here? What? This is in touch with each other, these are in touch with each other, but this and this are not directly touching each other. So, you cannot say that here molecularity is equal to 4. No. So, in most of the reactions, generally you could say that molecularity cannot be more than 3. It cannot be more than 3. Why? Because the reactants cannot be in direct touch with each other. Right? Yes, it is very difficult. It is very typical. So, we say that maximum molecularity that could be present in a particular reaction is 3. Perfect. Now, we are going to read something about molecularity. It is a theoretical concept. It is the number of molecules taking part in one-step reaction. Very important, in one-step reaction. It is only defined for one-step reaction of a chemical reaction. It is the number of molecules colliding. It is the number of molecules colliding simultaneously in a one-step chemical reaction. And the maximum number of molecules that could collide with each other are 3. 4 molecules are very difficult to collide with each other simultaneously. That is the reason it can have only maximum value 3. Since the probability of simultaneous collision of more than 3 molecules is very rare, it is very rare, so molecularity does not exceed the value of 3. Molecularity is always a positive quantity. It cannot be equal, it cannot be 0. 0 means that no reactant is present. Then how are you defining the molecularity? Right? Yes. So molecularity is only positive value. It cannot be negative. It cannot be negative. It cannot be 0. It cannot be 0 or fraction. Okay? Or fraction. Perfect. Now, one more example. Now I know that I have a single step reaction. I can define its molecularity, and the molecularity will be equal to the stoichiometric coefficients of one reactant, or if there are 2 reactants, then the sum of the stoichiometric coefficients of the reactants, right? Yes. Now, if I give you an example, you have to give me the molecularity of that particular reaction. I have H2 plus I2, which gives me 2HI. I have H2 half plus half I2, which is giving me HI. I have 2H2 plus 2I2, which is giving me 4HI. This is the same reaction. You can see, ma'am, it is the same reaction, right? Only the stoichiometric coefficients are different. So, its molecularity would come out to be 1 plus 1, 2. Since all are single step reactions, individual reactions, these are not mechanisms, these are single step reactions. So according to this, the molecularity should be equal to 1, and here the molecularity should be equal to 4, right? Yes. So ma'am, just tell me, ma'am will not tell, you will tell me that which of these molecularity is true and why. Are all these three molecularities correct, or only one of them is correct, or only two of them is correct? You have to think. Pause the video and just think about it. Here is the most important point. Whenever you talk about molecularity, you have to change your reaction to the most stable, balanced reaction. If you see here, you have the whole number here, you have whole number here, and you have whole number here, right? It is the most simplified form of the reaction. So only and only this molecularity is true. These two molecularities are not true, because here the stoichiometric coefficient is half, which is a fraction, which is not the most simplified form. If you see here, you can take 2 common. That is the reason this cannot be your molecularity. So molecularity can be defined in the most simple form, simplest form of a particular balanced chemical reaction. Okay, this is very important. Perfect. Molecularity is gettable from stoichiometric coefficients of elementary reactions. Perfect. To get the molecularity, we must take the smallest integer. Very important, my dear students. You should take the smallest integer value of the stoichiometric coefficients of the individual reactant, and thereafter we need to get the sum of the stoichiometric coefficient. I hope you got the point. Perfect. Very good. Let's move forward. For elementary step, order and molecularity are numerically equal. This is an important point. If you talk about an elementary reaction, for an elementary reaction, I told you that order can be equal, will be equal to the stoichiometric coefficient. Now, if you have 2A to B, then you would say, ma'am, molecular, and it is an elementary reaction, molecularity would be 2, and I can say that order will only also be equal to 2. We talked about this. Yes, ma'am. If you talk about, let's say 2A plus B gives you C. What will be the molecularity? 2 plus 1, 3. And what will be the order? Ma'am, again, order with respect to A is 2. Order with respect to B is 1. So overall order would be 2 plus 1, which is again 3. So for elementary reactions, order and molecularity are equal. But for complex reaction, you can only define order, you cannot define molecularity, right? Yes. Order of a one-step reaction cannot be fraction. Yes, from here we can say that it will never be fraction, because since it will be equal to molecularity, so it cannot be a fraction. Perfect. So this is how you understand the difference between order and molecularity, and you are asked 100 lots of questions from this particular topic. I hope it is understood to you. Perfect. Let's move forward. Now, a multi-step reaction is the assembly of many one-step reactions. The slowest step in the multi-step reaction is actually the rate-determining step. Now we are here at the multi-step reactions. We just talked about elementary reactions. Now we are going to talk about the multi-step reactions. If you have multi-step reactions, how are you going to study those, and how are you going to calculate the order of the reaction? Imagine you have a reaction. Imagine first, before understanding this, I would like to discuss a event with you, okay, a condition with you. I am talking about a marathon, okay. You are just running in a marathon, okay. You have many athletes, right? Usain Bolt you have, and you have me, who runs so slow that anyone would be a winner in front of me, okay. So you are running a marathon, and you have two members, Usain Bolt, I don't know his name, so I'll write Usain Bolt, and Anushka ma'am, okay. And you know that I'm very slow, so I'll write it here, slow. You have to run the marathon. Yes, so this is the marathon, and I am talking about that marathon where it takes place in partners, and one of the partner would run with that mashal. I think we call it what we call, I don't know its name, mashal, I guess. Yes, and then you hand it over to your partner, and then your partner would run, and eventually whoever runs fastest reaches the end point is the winner. Imagine this is my team, right? This is my team. He is the fastest, and my dear students, I am the slowest, okay. Now be it how fast Usain Bolt runs, if I am running slow, we will never win. If I am running slow, we will never win. If I run fast, then we can win. That means that the person who is the slowest actually decides you will win or lose, right? Yes, it's not the fastest person who decides you will win or lose. Be it Usain Bolt give his 100%. If I am running slow, then we'll never win. right? Yes. So what can we say? That the person who is the slowest is actually the deciding factor. I am the deciding factor. I will decide we will win or lose, right? Yes. So like this only in a mechanism. In a mechanism, you have many steps, and the step which is the slowest of all is actually your rate determining step, and from there you give your rate law and you calculate the order of the reaction. Okay, so from here I can say that from the mechanism I have to find which of the following is the slowest step, and that would be the rate determining step, and according to that particular step I will give the rate law. Okay, yes, I hope you just understood some of it. When we'll solve a question, you'll understand it more clearly. So the slowest step in the multi-step reaction is actually the rate determining step. Perfect. Let's move forward. We'll talk about a example. Now, in this example, just a second, my dear students. Yes. Here is the question. Yeah. This is the question. You have 2NO plus Cl2, which gives you 2NoCl. This is the reaction. You have 2NO plus Cl2 is giving you 2NoCl. And this is the mechanism. This is the mechanism. And in the mechanism, you are actually always given that which is the slowest step. So if I see, I can say that this will be my rate determining step. RDS, this would be my rate determining step. If this is my rate determining step, then the rate law will be written according to this. Okay, so rate law, that is R, will be directly proportional to the concentration of reactants, which is NoCl2 power 1 and NO1, right? Yes. I'll remove the proportionality. I'll get K, NoCl2 and NO. Now, what you have to understand here is that, see my dear students, NoCl2 is getting formed, is getting used here, and in this reaction it is getting formed here. This means that it actually does not exist. It was formed during the mechanism and it is used in the mechanism. It neither exists in the starting nor exists at the end. That means it cannot be present in your rate law. This is your intermediate. What is the intermediate? That is formed in the reaction and is also consumed in the reaction. Okay, and intermediates cannot be present in your rate law. So here you are going to write that NoCl2 is intermediate. It is an intermediate. It cannot be present in the rate law. So how are we going to vanish this intermediate, right? Yes, this is how you're going to do. You have the above reaction. You see that it is a equilibrium reaction. So we know how to write the equilibrium constant. Here we are going to write the equilibrium constant, which is K equilibrium will be equal to concentration of products, that is NoCl2, divided by concentration of reactants NO and Cl2. From here I can find the value of NoCl2. So value of NoCl2 would be equal to K equilibrium into NO into Cl2, right? Yes, use this in this rate expression. Okay, I'll use this. R will be equal to K into K equilibrium, K into into NO into Cl2 into NO again, right? Yes. So this can be written as C. This K and this K equilibrium, both are constants. 2 into 2 will give you 4. That will also be a constant value. Yes. This means that I can name it as a new constant value, K dash. Yes. So you can write that rate would be equal to K dash into NO whole square and Cl2 power 1. So my dear students, what is your overall order? What is your overall order? Order is, ma'am, 2 plus 1, which is equal to 3. Order with respect to NO is 2 and order with respect to Cl2 is 1. This is your final order which you have calculated. This might or might not be equal to the order given in the above reaction, but this is how you are going to calculate your order. Okay, yes. So what are you going to do? First, find out the rate determining step, that is your slow step. Write the rate law, find the intermediate. Now you have to replace the intermediate. You have to replace the intermediate by calculating the equilibrium, K equilibrium value. Use that value in the rate law expression and you will get your order. Okay, so this is how you will solve all these questions. Perfect. Very good. If you understood this, then you can solve the question, which is, where is it? Just a second. Huh? I did write the mechanism, my dear students. Just a second. Okay. Okay. We've moved forward a lot. Okay, here is the other question. Now solve the question, pause the video and solve the question. This is your mechanism and this is your reaction. 2O3 gives you 3O2. Okay, this is your final initial reaction. This is the mechanism. You have to find the order. How are you going to solve this question? First of all, you have to find the slowest step, which is this step. So you will say, ma'am, this is the rate determining step, right? This would be a rate determining step. So ma'am, rate law would be equal to K into O3 into O. If I see here, which is your intermediate? Ma'am, O is my intermediate, right? Yes, so you will write that O is the intermediate. If O is your intermediate, this means that you have to replace it. Yes, so we'll see that this is a equilibrium reaction. So K equilibrium would be equal to O2 into O divided by O3. So O concentration would be equal to K equilibrium into O3 upon O2. You have to use this expression here. Yes, so you will write Kr is equal to K into O3 into K equilibrium into O3 upon O2, right? Yes. Now just write the final expression. Rate would be equal to K into K equilibrium would give you some K dash constant. Yes. O3 whole square. And this would be O2 power minus 1. So what do we see? Ma'am, overall order would be equal to 2 minus 1, which is equal to 1. Overall order will be 1, but the order with respect to O3 is 3 and the order with respect to O2 is, my dear students, minus 1. It is not 1 or any fraction, it is a negative value. So this is how you calculate the order of the reactions, right? Yes, I hope you got this. So you get these type of questions as well. So you have to solve these type of questions. Perfect. I hope you got it. Let us move forward. Okay, we talked about molecularity. We talked about this. Perfect. No issues. Now we are going to solve some questions. Okay. So here are some points which we are going to study first. Rate law for the multi-step reactions. Second step itself is a elementary process for which order and molecularity are equal. The intermediate can't be present in the overall rate equation. I said you intermediate cannot be present. The rate of the overall reaction is equal to the rate of the rate determining step, but the rate constant of the overall reaction may not be equal to the rate constant of the rate determining step. I hope you got it. Yes, ma'am. For one-step reaction, the order corresponds to the stoichiometric coefficients. If the order is found to correspond to the stoichiometric coefficient, the reaction may or may not be a one-step reaction. Okay. Yes. Let's move forward and solve some questions. Okay. Here is your first question. Whatever we have discussed till now, you have to solve these questions according to those. Pause the video, try yourself, and then see ma'am's approach. Okay. First question says the differential rate law equation for the elementary reaction, this would be. We can write it very easy. Ma'am, if we have a reaction, then rate would be equal to, since A is a reactant, minus dA by dt, stoichiometric coefficient is 1. This would be equal to minus 1 by 2 dB by dt. Right? Yes. And ma'am, since it is a product, so 1 by 3 dC by dt. And ma'am, this would also be equal to K into A if it is a single step reaction. Elementary reaction, it's given that these are it is an elementary reaction, so A power 1 and B power 2. So let's see which is the right expression. Minus dA by dt minus 1 by 2 dB by dt plus 1 by 3 dC by dt, Ka power 1 and B 2. So ma'am, option C is the correct answer, right? Very good. Let's move forward. We'll do the other question as well. Second question is on your screen right now. Try it and solve yourself. The rate of the reaction is expressed in different ways as follows, and you have to tell me the reaction. Which of the following is the reaction? Okay, let's see. Plus 1 by 2 dC by dt. If I see plus, this means that C is a product. C would be a product, and since it's divided by 1 by 2, it means its stoichiometric coefficient should be 2. Minus 1 by 3 D, ma'am, means minus indicates that D is a reactant and its stoichiometric coefficient is 3. Plus 1 by 4, ma'am, this means A is a product and its stoichiometric coefficient is 4. If we talk about B, then ma'am, B and its stoichiometric coefficient negative, so 1, and this is your reaction, that is B plus 3D will give you 2C plus 4A. So B plus 3D will give you 4A plus 2C, that is option B will be your correct answer. Very good. Let's move forward. Next question, my dear students. Next question says that in the reaction A plus 2B gives you 6C plus 2D. If the initial rate is something, what will be the value of minus dB by dt? So if you find out R rate value, you can calculate dB as well, right? So if we see, then we can say, ma'am, rate will be equal to minus dA by dt, and this would be equal to minus 1 by 2 dB by dt, right? These both would be equal. You understand this concept? Yes, ma'am. Now see, the value of minus dA by dt is 2.6 or 26. It might be 2.6. Okay, this is 2.6 into 10 raised to the power minus 2 molar. So I can say that 2.6 into 10 raised to the power minus 2 will be equal to minus 1 by 2 dB by dt, and I have to find the value of minus dB by dt. So you have to cross multiply 2 to this. Then you can say that minus dB by dt will be equal to 2 into 2.6 into 10 raised to the power minus 2, which is 2 to 12 to 15.2 into 10 raised to the power minus 2 molar. Right? Yes, per second as well. So the correct answer would be 5.2 into 10 raised to the power minus 2 molar second inverse. That is option C would be your correct answer. Right? Yes, I hope you got this as well. Let's move forward to the next question. Next question, my dear students, just read the question and solve it. The question says the rate of the reaction is expressed in different ways as follows. The rate of a reaction, the question is different. You have to write the unit of rate constant. Okay, you have to tell me the unit of rate constant K. Okay, so ma'am, unit of rate constant K is given by mole 1 minus n liter n minus 1 second inverse. So mole 1 minus n liter n minus 1. Is there any such factor? Mole 1 minus n liter mole 1 minus n liter n minus 1. No, this is not right. Mole 1 minus n. Okay, liter n minus 1. Mole 1 minus n liter n minus 6. Yes, my dear student, this should be n. So option D will be your correct answer. Mole 1 minus n liter n minus 1 and second inverse. That is option D will be your correct answer. Okay, just suppose all the A's are n. Okay, perfect. Let's move forward to the next question. Next question. See the question and solve yourself. Which of the following statement is incorrect? You have to tell which of the following statements is incorrect. Okay. Yes. Let's see. Unit of rate of disappearance is molar second inverse. Right? Yes. So which of the following statement is incorrect? First is unit of rate of disappearance. See, it is a rate. It would be molarity per second. So molar per second, this is absolutely correct statement. Let's talk about the other. Unit of rate of a reaction. Again, my dear student, it is a rate. So its unit would be the same. Molar per second inverse. Yes, ma'am, this is absolutely right. Unit of rate constant K depends on the order. Yes, it actually depends on the order. Next is unit of K for first order would be molar second inverse. No, for the first order reaction, the unit of rate constant is the second inverse. Right? Yes. So the incorrect statement would be option D. So the incorrect statement would be option D. Perfect. Let's move forward to the next question. Next question is on your screen. Just read the question and try yourself. So the rate constant of a reaction depends on. So what all the factors are there on which the rate of a reaction depends? Ma'am, rate constant. Obviously, it depends on temperature. Yes, ma'am, it depends on temperature. Does it depend on the pressure? No, it does not depend on the pressure. Does it depend on the extent of the reaction? No, it depends on the nature of the reaction, not extent of reaction. Initial concentration of the reactant? No. So, my dear students, only and only option A is correct. Perfect. Let's move forward. Next question. Next question is, okay, in the following reaction, how is the rate of appearance of the underlying product related to the rate of the disappearance? Okay, I'll underline it. You have BrO3 minus and Br2. So you have to find the relation between their rates. Okay, so if I see, then rate would be equal to, ma'am, it is a reactant BrO minus O3 minus, so minus D concentration of BrO3 minus divided by DT, and this would be also equal to the product, so this would be a plus sign. Coefficient is 1 by coefficient is 3, so 1 by 3 D concentration of Br2 by dt. So let's see which is the correct option. So if we see, then minus D BrO3 minus by dt would be equal to 1 by 3 plus 1 by 3. Yes, ma'am, option C would be a correct answer. Perfect. Let's move forward, my dear students. Next question is, which of the following statements is incorrect? You have to tell that which statement is incorrect. Okay, let's read the statements. First is, a second order reaction must be a bimolecular elementary reaction. What does the first session say? First option says that if the order is 2. If, my dear students, order is 2, I can say that it could be an elementary reaction or it could be a complex reaction. I don't know it is an elementary reaction or a complex reaction, only order is given. And it says that it must be a bimolecular reaction. Bimolecular means that molecularity should be equal to 2. So if it is an elementary reaction, then molecularity will be equal to 2, but if it is a complex reaction, then molecularity cannot be defined. So my dear students, this statement is wrong. You cannot say that if order is 2, then it should have molecularity 2. If it is a complex reaction, it will not have 2 molecularity. Perfect. Next, a bimolecular reaction means that molecularity is 2. This indicates that reaction is elementary, and for elementary reactions, molecularity is always equal to order, and that would be equal to 2. So a bimolecular elementary reaction must be a second order reaction. Yes, this statement is correct. Zero order reaction must be a complex reaction. Yes, because zero order reaction will have molecularity equal to 0, which is not possible. Molecularity is not defined for a zero order reaction. It is always a complex reaction. So ma'am, third statement is right. Fourth statement, first order reaction may be a complex or elementary reaction. Yes, order can be one for a elementary reaction also, as well as for a complex reaction as well. So only one statement is wrong, which is option A, and it was a very good question. So you should understand this question. If you are not thorough with this question right now, just rewind the video and watch it again. Perfect. Let's move forward. Next question, my dear students. The molecularity of a complex reaction given below is. Now you have been given a reaction, and also you are told that it is a complex reaction, and they are asking you about its molecularity. If it is a complex reaction, the molecularity cannot be defined, right? It cannot be defined. So the correct answer would be option D. It does not have any meaning, right? Perfect. I hope you got it. Perfect. Let's move forward. Next question. Next question. Okay, we've discussed this. We have discussed this. So let's move Now my dear students, we are going to talk about the different types of order of reaction. We have discussed how to calculate the rate, how to calculate the rate constant, how to find out the order of the reaction if we are given the rate constant. What will be the order and molecularity for a single step reaction, for a multi-step reaction? How are we going to calculate the order? How are we going to calculate the molecularity? All this we have discussed. Now we are going to discuss about particular order of reactions. That is, if you are given a zero order reaction, then what all you can conclude from that factor. Okay, yes. So what all you have discussed right now, you are going to use all of it in this one particular topic. So let's start. It is going to be amazing. So my dear students, first is zeroth order reaction. If you are given a zero order reaction, this means that ma'am, N would be equal to 0, right? N is your zero order reaction. So ma'am, N would be equal to 0. So what I have learned till now, if the reaction is sum Na gives me product B, then I would say that rate law is given by rate would be directly proportional to A. It is a reactant raised to the power N, where N is the order of the reaction. I am telling it is a order of reaction. Okay. Okay, perfect. So ma'am, R is directly proportional to A power N, and N I have defined as order of the reaction. Now, since N is equal to 0, so ma'am, R is equal to K A power N. So R would be equal to K A 0. Now anything raised to the power 0 is 1, right? We know that x raised to the power 0 is equal to 1, 2 raised to the power 0 is 1, everything raised to the power 0 is 1. So I can say that rate would be equal to some k constant. This is the first derivation or first discovery that we have found out from n zeroth order, that for a zero order reaction, the rate of the reaction is constant. The rate of the reaction is constant. It does not depend on the concentration of the reactant. Imagine if you are asked to plot a graph. If you are asked to plot a graph, right? Yes. For a zero order reaction, if you are asked to plot a graph between the rate and concentration of reactant. Okay, yes, rate and concentration of the reactant. You can see that rate is constant value. K will have a constant value at a particular temperature as long as the temperature is constant. It does not depend on the concentration of reactant. Yes, ma'am. So rate will be constant, be it any concentration of your reactant. If initially you have a lot of reactant, or at the end you have only a small amount of reactant, it does not matter. The rate will be a constant value. So the graph would be something like this. It would be a straight line, right? And since reactant's concentration with time decreases, so we will study this graph. How? We'll study this graph like this, that as you decrease the concentration of the reactant, your rate will be constant. It does not depend on the concentration of the reactant. This is the first thing that we have derived from this particular topic. Perfect. Yes, ma'am. We understood this. Now my dear students, now is the best part that we are going to discuss, and that is we are going to derive the integrated rate law of zero order, and then we will be calculating n number of things from that one integrated rate law, right? Yes, perfect. I hope you got this point. Let's move forward. The unit of rate constant provides the overall order of the reaction. I hope you get this. So rate constant K is equal to mole 1 minus n liter n minus 1 second inverse. For zero order, n would be equal to 0, so K would be equal to mole liter inverse second inverse. So for a zero order reaction, the unit of your rate constant would be this. Perfect, no issues. Let's move forward. Next is the rate law provides the variation in rate with concentration. The rate law actually tells you that how your rate will depend on the concentration of reactant. We know that rate depends on the concentration of reactant, but how does it depend? That is given by the rate law, right? Yes, maybe R is directly proportional to the reactant's concentration raised to the power 1, or R is directly proportional to the reactant's concentration raised to the power 2. That depends on the order of the reaction, and this is given by the rate law. Perfect. Next, my dear students, in zeroth order reaction, the rate is independent of concentration. We just drew the graph, rate, and this is concentration, and it was a Straight line, right? So it is independent of the concentration and remains constant throughout the reaction. Perfect. Let's move forward. We just drew the graph. Perfect. Since the rate is not defined at zero concentration, you cannot define the rate at zero concentration. If you don't have reactants concentration, then you cannot define it, right? That is the reason that we drew this graph, and ma'am just didn't touch this point here, because this means that concentration of the reactant is zero, and we cannot talk about the rate at zero concentration of your reactant. Since there is no reactant concentration, there would be no rate, right? That is the reason we don't touch this line here. Perfect. This is what is given here. Perfect. Okay. Since the rate is not defined at zero concentration of reactant, the horizontal line must not be in contact with the y-axis. Perfect. Next. In a zeroth order reaction, the concentration decreases linearly with time. Now we are going to discuss about this. Okay, yes. My dear students, always remember that if you have a reactant, then with time that reactant will definitely decrease with time. Yes, you know that if you have a lot of reactant, it will definitely be consumed and it will decrease with time. But how will it decrease? That we are going to find out by the integrated rate law. Okay, yes. So now we are going to calculate the integrated rate law. The unit of rate constant must remain the same in the rate law. I think you have understood this. And the integrated rate law. Perfect. Now we are going to calculate the integrated rate law. Integrated rate law. Integrated rate law. Now, imagine for integrated rate law, we are calculating for a zero order reaction. So, for a zero order reaction, there are a few steps which you have to understand to find the integrated rate law. Zero order I am deriving, for the first order you are going to derive. Okay. Now, my dear students, for zero order n is equal to 0, we know the reaction is Na, that gives you B. So, rate law, first would be rate law, and that is given by R is equal to K A power 0, right? Yes, this will be your first equation. This will be your first equation. Second equation, which we found out rate, right? Instantaneous rate also we calculated, which was R is equal to minus dA by dt. This is how we are going to write this. Perfect. Now, my dear students, this is your second equation. So, what are you going to do? Ma'am, just equate first and the second equation, because both are talking about the same reactions rate. Yes, perfect. So, now what can we say? We can say that equating 1 and 2, K A power 0 would be equal to minus dA by dt. Right? Yes. Just cross multiply. K A power 0 would be 1. So, K dt would be equal to minus dA. I'll just put this side. Yeah. Minus K dt will be equal to d of A. Now, what are you going to do? You have to integrate it. So, now we are going to integrate it. So, integrating. Now, we are going to integrate it. Integrating on both sides, minus from 0 to t time, which is minus K dt, and this would be equal to from 0 to from initial concentration, that is A naught, to A at some time t. So, this would be dA. Now, I'll just define the factors. Okay. What is A naught? A naught is the initial concentration of reactant. Initial concentration of reactant at T is equal to 0. Okay. What is AT? AT is the concentration of reactant at time T, at some time T. So, say when you will integrate them, what all things are you using, right? For my NEET students, I am telling you this. I think JEE students knows this, but for the NEET students, I want to tell you that integration of dx is always equal to x. Okay, integration of dx is always equal to x. So integration of dt will be equal to t, and integration of dA will give you a. Okay, so in using this, I will integrate. K is a constant, so minus k dt from 0 to t is equal to a naught to at dA. Using that, integration of dx will give you x. What can you say? Minus k t from 0 to t. Now, when you put limits, the lower limit will be here and the upper limit would be here. So, accordingly, ma'am, this would be a from a naught, the lower limit, to the upper limit, which is a of t. Okay. Now, when you put these limits, what will it take place? Minus k. See, upper limit t minus lower limit 0. This will be equal to upper limit a of t minus lower limit, which is a naught. This is how you put the limits. Upper limit minus lower limit. Okay. Yes, ma'am. Perfect. Now, my dear students, you just have to solve this. This would be minus kt, which is equal to at minus a naught. So, a naught. So, I can say that a naught would be at plus kt, or I can say a of t would be equal to a naught minus kt. Right? Yes. So this is your integrated rate law. This is your integrated rate law for zero order reaction. This is integrated rate law for zero order. Okay, so this is your integrated rate law for zero order reaction. You have to memorize this, my dear students, that concentration of your reactant at any time t will always be equal to the initial concentration at 0 time minus k, which is your rate constant, into the time which you have the reaction has taken place. Okay, this is your integrated rate law for zero order reaction. You need to memorize this. Perfect. I hope you got it. Now, my dear students, we are going to plot a graph. Now we are going to plot a graph. So graph would be equal to a of t is equal to a naught minus kt. Right? Yes. Use the straight line equation. Straight line equation would be equating it by y is equal to c minus mx plus mx. Right? If I see here, y axis would be a of t, x axis would be t, and intercept c would be equal to a naught, and slope will be equal to minus of k, which is by m. Right? So you will have a negative slope. You will have a negative slope. So now, my dear students, you have to plot a graph. This is y, this is x axis. So at y axis you have to put a of t. At x axis you have to put t. Right? And it should be a negative slope. Right? Negative slope. So here slope is equal to minus k, and intercept would be a naught. So this is the intercept and this is equal to a naught. That is your initial concentration. So this is the graph between the concentration of the reactant and time. And if you see that as the concentration of the reactant is decreasing, time, with increasing time, your concentration of reactant is also decreasing. Right? Yes. So ma'am, with time, the concentration of reactant decreases. Perfect. Yes. I hope you understood this. This you can derive from the integrated rate law. Perfect. So this is how you calculate the integrated rate law. You need to remember this, my dear students. You need to understand how you are going to plot the graphs. Perfect. Yes. So you can write this and then we will move forward. Okay, let's start again. Now, next is half-life period. What is half-life period? First, we have to understand this. Imagine your reaction is taking place. You had some A naught concentration initially. After some T time, now you are left with half of your reactant's concentration. So, the time at this point will be your half-life. So what is half-life? Half-life is the time period when you are left with half of your reactant's concentration, right? Yes. So first let us understand the definition of half-life. The time required for the concentration of the reactant to become half of the initial value is known as the half-life of the reaction. A reaction can have infinite number of half-lives and the magnitude of the half-lives may not be the same. Now I am going to make you understand this concept. Imagine I had some reactant A with 100 moles of the reactant, right? Yes. So what will be its after first half-life, what amount of reactant would be left, ma'am? If they were 100 moles, then you would be left with 50 moles, right? Next half-life would be, ma'am, when you will have 25. Now half of this is 25. Half of this would be 12.25, right? Yes, 12. 12.5, 12.5, I'm sorry, 12.5, and this would be 6.25 and so on, right? Yes. So it according to this we can see that we can have infinite number of half-lives. Yes, the time taken here would be t half, the time taken would be t half, the time taken would be t half, time taken would be t half, but it is not necessary that this t half, this t half, this t half and this t half are equal. No, all the half-lives would be different, all the half-lives would be different. Okay, yes. So this is what is told you by the half-life factor. Perfect, very good. Now we are going to calculate the half-life. How are we going to calculate the half-life? My dear students, at half-life I can say that t time would be t half. I would say t time would be t half. Yes, ma'am. Next, what can I say? That A naught will be the initial concentration. Initial concentration of reactant, and A T, which would be equal to A naught by 2, right? At some time T half would be half of the initial concentration. This would be the concentration of reactant after T half time, right? Yes. Now using the integrated rate law which we derived just a few seconds earlier, A of T would be equal to A naught minus KT, right? Yes. What is the value for AT? A naught by 2. So ma'am, this would be A naught by 2. This would be equal to A naught minus K into T half, right? Now you are supposed to bring this here and this here. So you will get A naught by 2 will be equal to K T half, and T half would be equal to A naught by 2K. Right? Yes. So this is the one other expression which is very important for you, because this is the T half for zero order reaction. This is the T half for zero order reaction. And we see that the T half value, that is your half-life period, actually depends on the concentration. It actually depends on the concentration of the reactant. The more the concentration of the reactant, the more time will be taken for its half-life to achieve. Similarly, if you have, you can say from here that if you have 100 moles, then this T half will be greater than this T half, because its initial concentration is 100, but for this T half, the initial concentration is 50. So yes, the half-life depends on the initial concentration of the reactant. So if this T half is, let us say, 10 minutes, if 100 moles takes 10 minutes to get converted into 50 moles, then 50 moles will definitely take 5 minutes, that is less than 10 minutes to get into 25 moles. Similarly, this T half will be less than this. So this is given by the T half expression. We can say that the half-life period of zero order reaction actually depends on the initial concentration of the reactant. Next question that you are generally asked is to plot the graph between T half versus concentration of the reactant. So what will you say? Ma'am, T half is equal to A naught by 2K. So T half is actually directly proportional to the concentration of the reactant, right? So the plot would be T half and there will be concentration of the reactant, right? So the plot would be, see, it is directly proportional, so the line would be something like this. You can say that this is Y is directly proportional to X, right? Yes. So straight line passing through the origin. Yes. So as your concentration of the reactant will decrease, T half will also decrease. Yes. So the half-life periods for a zero order reaction are not equal. They depend on the initial concentration of the reactant. The more the initial concentration, the more will be the T half, right? Yes. These are the conclusions that we have made from only and only one thing, which was the integrated rate law. Yes. And all the factors which I am underlining are actually very important. Perfect. Let's move forward, my dear students. Now we are going to talk about what are the reactions which actually are of zero order, right? You should know some examples of zero order reaction. So the first example of zero order reaction is the most of the heterogeneous catalysis. Let's talk about organic now. When you talk about organic reactions, you might have studied the hydrogenation of alkenes, right? You use some catalyst, nickel. You use some catalyst, nickel, right? Yes. And you get alkanes. Yes. So these reactions are of zero order. These reactions are an example of zero order. You also have one more example of zero order, which is your photochemical reactions. Which are your photochemical reactions? Let's say you have an alkane and you are adding Cl2 gas in presence of sunlight. So you get free radicals. I guess you have learnt this. If not, then you can understand this. These are catalytic reactions. These are free radicals formed and you get somewhere here chlorine or you get chlorine here, right? This is another example of your zero order reaction. This is another example of your zero order reaction. Perfect. Very good. So we have discussed everything about zero order reaction. So now we'll move forward. Let's try a question that how to apply the laws that we have discussed yet in numerical point of view. First is calculate the time needed for the 70% completion of a zero order reaction. You are given T half, which is equal to 30 minutes. So for zero order reaction, I know the integrated rate law. So first of all, I'll write the integrated rate law. A of T is equal to A naught minus K T, right? Yes. Now, I am given T half of the reaction, okay ma'am, and you have to calculate the time needed for 70% completion of the reaction. Your reaction is, my dear students, 70% completed. So, 70% reaction is completed means that A naught was the initial concentration and A of T is the concentration after 70% of your reactant is consumed. If 70% of your reaction is consumed, then how much reactant is left? Ma'am, it would be A naught initial minus 70% of it is consumed. That means 70 upon 100 of A naught, right? Yes. So you can calculate this. This would be equal to A naught minus A naught by 10, 7. 10 minus 7 is 3 A naught by 10, right? Perfect. No issues. Yes. So now you can say this will be equal to 3 A naught by 10 will be equal to A naught minus, you have to calculate the time. Now what will we do for the rate constant K? I know that I am given what? T half, and I know the expression for T half. T half is equal to A naught by 2K, right? So what will be the value for K? K would be equal to A naught by 2 T half. T half is 30 minutes. So A naught by 2 into 30. So we are going to use it here. So this would be A naught by 2 into 30. So A naught cancelled. So you will get 3 by 10, which is equal to 1 minus 1 by 60. So you just have to solve it, my dear students. TTT. Okay, so you have one reaction, you have T time, you can calculate and just tell me the answer in the comment section, right? Yes, so this is how you are going to use the integrated rate law for the zero order reaction to solve the questions. Perfect. Let's move forward. Next question. Okay, now we are going to talk about the first order reaction and then we'll talk about the practice questions in total after studying this particular topic. Okay, now first order reaction, ma'am, exactly same as zero order. We'll follow all the steps like in the zero order. Okay, so now if you have a first order reaction, this means that, ma'am, n is equal to 1, right? So the integrated rate law would be k into a 1 power 1. Yes, so r is equal to k a power 1. Now what is going to happen, ma'am? This is your rate law. This is from rate law. This would be first equation, my dear students. Yes, what will be the second equation? For second equation, ma'am, rate would be equal to minus dA by dt, right? Yes, so this would be your second equation, so just write it to be second. Now my dear students, 1 will be equal to 2. Yes, before this I just want to know that what will be the unit of rate constant K. I hope you remember that unit of K rate constant would be mole 1 minus n liter n minus 1 second inverse. So ma'am, this would be second inverse. So any value which has a rate constant equal to second inverse unit, it will be the rate constant for the first order reaction. Okay, now we can discuss about this. If 1 is equal to 2, then ma'am, K A would be equal to minus dA by dt. So now, my dear students, you are supposed to integrate it accordingly like you integrated in the zero order, and then you will find a relation and you will get the integrated rate law for the first order reaction. Okay, so you are going to move with me step by step. Now, multiply this k dt here and bring this a here. Okay, so what will be? This will be k dt and this would be minus dA by a. Perfect. Let's write this. I'll bring this minus as well here. K dt is equal to dA by a. Okay. Now what are we going to do? Ma'am, we are going to integrate it like we integrated initially from 0 to t, from a naught to a t. So integrating both sides, we get minus k. K is a constant, so dt from 0 to t. This will be equal to integrating from a naught to a of t dA by dt, dA by a. So what expressions, what integrating factors are we going to use for my NEET students, my dear students, for my future doctors? We are using that integration of dx will give you x. First thing, and second, integration of, my dear students, dx by x gives you ln of x. This gives you ln of x. Whenever you have integration of dx by x, it gives you ln x. So these two things we are going to use here. Now, first would be, ma'am, minus k. See, dx integration is x, so integration of dt would be t from 0 to t. This would be integration dA by a, that is dx by x will be ln a, ln x. So this would be ln a from a naught to a t, right? Upper limit minus lower limit, putting the limits, it would be minus k t minus 0. This would be ln of a of t minus ln of a naught, right? Yes. Now, my dear students, we are going to use some log properties as well. What log property are we going to use? Ln of a minus ln of b, right? So I am going to use the property ln of a minus ln of b will always give you ln of a upon b. Okay, so if here I have ln of at minus ln of a naught, I can write it as ln of at by a naught. So we are going to write it minus kt. I'll write it with white. So this would be minus kt. This will be equal to ln of at by a naught. Okay, clear? Yes, ma'am. Now, my dear students, you have to incorporate this negative sign into this. Okay, so how are we going to do this? We'll do this initially. First you can find one expression. What am I going to use again? You have to see, using, whenever you have to convert ln of x into some power. So converting ln of x, you can write it to be, if ln of x is equal to a, if ln of x is equal to a, then you can say that x is equal to e raised to the power a. Then you can say that x is equal to e raised to the power a. So using this, we can convert this into this. Let's convert it. Ln of x, here x is a of t by a naught. So a of t by a naught will be equal to e raised to the power minus kt. So I used this expression into this. So I can say that a of t is equal to a naught e raised to the power minus kt. So this is the very, very important expression that again you should know about the first order reaction, that the concentration of your reactant with time, yes, it decreases, but this time it decreases exponentially. If you saw in the zero order reaction, it was decreasing linearly, but here the concentration of the reactant is decreasing with time exponentially. So if you are asked to plot a graph, then what are you going to say? For the graph, we would say that concentration of the reactant at any time t to the time t would be decrease, but exponential decrease. So ma'am, the decrease would be something like this, right? For zero order reaction, it was linearly decreasing, it was a straight line, but for the first order reaction, it is a exponential decrease, and we just derived how it is an exponential decrease, right? Yes. So this is the first expression that we have derived yet. Now we are going to derive many more expressions which you need to remember. Now again, bache, I am going to start from this point only. I am going to use this expression and we are going to derive something else. So using this again, minus kt is equal to ln of a of t by a naught. Okay, yes ma'am. Incorporate this negative to the power of this. What will it happen? Ma'am, kt will be equal to minus ln at by a naught. Okay, my dear students. Now, what are we going to use here? Whenever you have something ln of x, using, I'll write it here, using, whenever you have something minus ln of x, you can write it to be ln x power minus 1, and you can write it to be ln 1 by x. So whatever the negative value is here, you can bring it to the power here, and then you can use it like this. Okay, so I am going to use this expression. So I can say that kt will be equal to ln at by a naught whole power minus 1, which can be ln a naught by a t. Right? We can write this. Yes. Now, my dear students, ma'am is going to use some other thing as well. Whenever you want to convert ln x to log 10 base 10, you have to multiply with 303. So log 10 base, this would be equal to 2.303 log x. So now converting this into log 10 base, I can say that kt is equal to 2.303 log of a naught by log of a naught by a of t. Right? Yes. So this is another expression. We'll just find out its final solution. This would be k is equal to 2.303 by t log a naught by a t. So this is another expression which you should remember, my dear students, how you are going to calculate the rate constant, for a first order reaction, right? Yes. So this expression is again important. Perfect. Now, what are we going to do next? Imagine you have a first order reaction. A is going to some product B. Initially, you had A moles, so you didn't have anything because this was at T is equal to 0. At T is equal to 0, the initial concentration of the reactant is actually A. So I can say that A naught is equal to A moles. After some t time, let us say X moles just reacted. So ma'am, this would be equal to A minus X. Yes, and this would have formed X. So I can say that A of t is equal to A minus X. I can say that A of t is equal to A minus X. Yes, ma'am. A of t is the amount of reactant left. How much amount of reactant is left? A minus X. And how much reacted? X. And how much formed product? X moles. Perfect. So incorporating this in this expression, can I write that K is equal to 2.303 upon T log value of A naught A upon A minus X, where X is the amount of reactant reacted, right? Yes. So again, my dear students, this is another expression which you are going to use extensively for the zero order reactions. Okay. Yes. So these are all factors, these are all expressions that we have derived for the integrated rate law of the first order reaction, which you will be using in your numericals. Right? Yes, you should know how you have derived them. You should know their expressions as well. These are only, you are talking about only one expression and you just calculated them in different ways. Okay, yes, perfect. So I hope you understood this. If not, then you have to go back and you have to just go through the whole video again. Right? Yes. So therefore the concentration decreases exponentially with time. I hope you remember we just calculated A of t is equal to A naught e raised to the power minus k t. And yes ma'am, the plot was A of t versus time. This was a exponential decrease. Next, therefore the reaction would be never be okay. 100%. Yes, my dear students, you have to remember this, that the first order reaction is never 100%. It is never 100%. You never touch these two with the x-axis or the y-axis. Okay, it never touches them. If you will keep on decreasing the concentration, if you calculate the half-lives as well, you will see that the reaction will never be completed. Okay, so first order reactions are never completed to 100%. Perfect. Let's move forward. Now we are going to solve a question, which is you have to calculate the expression for T half. You have to calculate the expression for T half for a first order reaction. So first pause the video and try yourself, and then I'll give you the expression. Till then I'll have some water, right? Yes. So calculate it, my dear students. Okay, let's start. Yes, ma'am. Again, exactly like the zero order. First, write the integrated rate law. I know the integrated rate law is K is equal to 2.303 by T log A by A minus X. We can use this expression, or you can use A naught by AT, one and the same thing. Perfect. Now, my dear students, I'll use A naught by AT so that you will not get confused. So, A naught by AT. Okay, now my dear students, if we talk about T, then I'll say that T is T half. A naught is the initial concentration. And what will be the value of AT, ma'am? It will be equal to A naught by 2, right? Yes. So put these in the integrated rate law. So ma'am, K would be equal to 2.303 by T half log A naught by A naught by 2, right? We can cancel A naught by A naught. What will you get? You will get K is equal to 2.303 by T half log 2. Okay, yes. You can say that T half is equal to 2.303 into log 2 by K. The value of 2.303 into log 2 is equal to, you can write K is equal to this value. If you multiply this, log 2 is 0.3. So you multiply it by 0.3, you will get 0.69 divided by K. Okay, yes, perfect. So this is divided by T half. I think this is only the calculation, 0.23 into 0.3, so this would give you 339. This would be 0, 339, 326, and you will get 0.9, yes, by t half, and this point would come here. Okay, so this would be 0.693 by t divided by k. Yes, so the expression would be this. Yes, ma'am, this would be the first expression. Also, the second expression could be k is equal to ln of 2. Ln of 2 value would also be equal to 0.693 only, and so this is the expression for the k value or t half value. Okay, so you can calculate it like this. So what can I say from here? What can I interpret from here? That t half for a first order reaction is 0.693 by k. That means can you see any term of initial concentration of the reactant? No. So what can we say? Ma'am, we can say that t half does not depend on the initial concentration of reactant. So this is very important. That is t half of first order does not depend on initial concentration of reactant, So half-life for a first order reaction is always a constant value. So half-life of a first order reaction will always be a constant value. So if you are asked to plot a graph, between t half versus concentration of the reactant, what would be the plot? T half, concentration of the reactant, it will be a constant value. It will not depend on the initial concentration of the reactant. This means that, ma'am, if you have 100 moles, then first half life T half would be 50. Then, ma'am, this would be 25, and ma'am, this would be 12.5, right? This T half and this T half. So since the half-life of a first order reaction does not depend on the initial concentration of the reactant, if the first half-life is 10 minutes, then my dear students, second half-life will also be 10 minutes. So this will also be 10 minutes, this will also be 10 minutes, and so on. So all the half-lives of a first order reaction are equal, and they does not depend on the initial concentration of the reactant. This is a very, very important thing to remember. Right? Perfect. So now we can say that for first order reaction, the half time is independent of the initial concentration of the reactant. Perfect. Let's move forward. The time required for any % completion of reaction is independent of the initial concentration. Yes, if the half-life is not depending on the initial concentration, then any % of reactions would not depend on the initial concentration of the reactant, right? Yes. Now we are going to apply all these concepts and practice some questions. So you have the first question. Show that for a first order reaction, time required for 99% completion is twice for the time required for the completion of 90% of the reaction. If you are able to do this question, all your first order concepts are clear. So now you have to pause the video and try the question yourself. Okay, do let me know in the comment section who all were able to solve this question on their own. So now let's start. We know for first order reaction, K is equal to 2.303 upon T log A naught by A of T. Right? Yes. Now, show that for the first order reaction, time required for 99% reaction completion. So 99% reaction would be T99%. I can write this. Rate constant would be K only. And my dear students, T would be equal to how much? Ma'am, 99% of the reaction is completed. So how much of your reactant is left? A naught minus 99 upon 100 of A naught, which is equal to A naught. 100 minus 99 is 1 upon 100, which is A naught by 100 is your reactant left. So the expression would be K is equal to 2.303 upon T 99% log of A naught upon A naught by 100. So cancel A naught by A naught, you will get K is equal to 2.303 by T 99% log of 100. Okay, this is your first expression. We'll say this is our first equation. Perfect. Now we are going to talk about the second expression, which I'll write by yellow color. Now, second is for the 90% completion. So if 90% completion, then T 90%. Yes, ma'am. And what would be the value for 80? This would be A naught minus 90 upon 100 of A naught. This would be A naught. Then 10 upon 100, which would be A naught by 10, right? Yes, no issues, perfect. So ma'am, expression would be K is equal to 2.303 upon T 90% log of A naught upon A naught by 10. A naught cancelled, you will get K is equal to 2.303 upon T 90% log of 10. Log of 10. This will be your second expression, right? Yes, you are supposed to say, find out that the time required for this 90% T for this would be equal to 2 times of this. Okay. So what are we going to do? Let's divide second equation by first. Let's divide second equation by first. So 2 divided by 1. What will we get? What is the second expression? K is equal to 2.303. K is equal to 2.303 by T log 10, T 90% divided by K is equal to T 99% log of 100, right? Yes, you can cross multiply them. Just cross multiply them. I'll write here 2.303 by K, and I'll write here T 99%. Okay, I'll write T 90% and I'll write K here, because rate constant is constant as long as the temperature is constant. So this will be cancelled out by this. So T 90% divided by T 99% will be equal to log 10 upon log 100. Okay, yes. Now, my dear students, log 10 is equal to 1 and log 100 is equal to 2. I hope you remember this. So, this is equal to 1 upon 2. So, what can you say? That T 99% is equal to 2 times of T of 90%. So, yes, ma'am, it is absolutely right and we have proved it. If you were able to prove this, then my dear students, your first order concepts are crystal clear, right? Yes. So, this is how you are going to solve these questions. Perfect. Let's move forward. Next question is on your screen. Now, my dear students, what if all the reactants and products in your first order reaction are gases? How will you solve the questions? Then we will talk about the pressure terms and not about the concentration terms. So here is the question and we are going to discuss about this question. Okay, you can read this question and then we will start. Okay, so now we see that when all your reactants and products are gases, then you cannot talk about their concentrations, right? Then you have to talk about their pressures. So now we are going to discuss about how to use the pressure in the first order integrated rate law. Okay, so now what is the expression? Again, my dear students, this is also a gas, this is also a gas, and this is also a gas, right? Yes. So now what are you supposed to do? Let us say this is your A reactant, which is giving you B product and is giving you C product. Perfect. Now, my dear students, what are you supposed to do? See, you have A reactant which is giving you B gas plus C gas. All of them are gases. So if you talk about the pressures, then at T is equal to 0, P initial will be the pressure and the total pressure would be because of the reactant gases, because you will not have product gases. So this will be nothing. At some T time, my dear students, you will have some Pi minus X pressure. You will have some X pressure here and here also X pressure. So if I talk about the total pressure, at T is equal to T time, the total pressure would be because of all the three gases present, that is reactant and product. So you will have to add all the pressures together and you will get your total pressure, because whenever you calculate the pressure, you calculate it total only. So initially it was only because of reactant, so P initial was the pressure of the reactant, but at time t you have reactant as well as product, so you calculate P total and that would be the sum of the pressures of all. So this will be equal to Pi minus X plus X, right? Yes, you get it. I hope you get it. Pi minus X, one more X. Yeah, perfect, right? Let's see what the question says. It says if P is the initial pressure of the reactant. Yes, ma'am, we put that. And Pt is the total pressure after time t. Pt is the total pressure which was calculated, which involves your reactants as well as products. From starting of the reaction, show that the rate constant is given by the expression. Okay, ma'am. Now, what are we supposed to do? You have P initial minus X. Use the integrated first order rate law. Ma'am, K would be equal to 2.303 by T log. This time, my dear students, you are talking in terms of pressure. So, at the place of initial concentration of reactant, you can write P initial divided by what was AT? AT was how much reactant is left, which was A initial minus X, or you could say P initial minus X. Yes, ma'am. So we can write it like P initial minus X. There's nothing wrong about it. Yes, since we are talking about gases here. Perfect. Now, my dear students, in your rate expression, you cannot involve X factor. You have to involve your P total factor. How are you going to involve your P total factor? From here, I can say that minus X plus X cancel. So P total is equal to P initial plus X. From here, I can find X value in terms of P initial and P total. So X would be equal to P total minus P initial. So using this expression here, what can I say? This would be 2.303 by T log P initial by P initial minus P total minus P initial, right? It's only maths, nothing big. You've done the chemistry part. It is 2.303 by T log P initial by P initial plus 2P initial minus P total, right? So this would be your final expression of the rate constant. Let's see, are we able to solve or not? 2.303 by T log P initial by 2 P initial minus P total. So 2.303 by T log P initial by 2 P initial minus P total. Yes, we have proved this, right? So this is how you are going to solve questions when you are given a reaction where only and only reactants and products are gases. So you have to calculate the rate constant in terms of your pressures, okay? And this is how you are going to solve. Let's do one more question and clear this concept purely, right? Yes. So now, my dear students, you have to solve this question. See how ma'am solved the first question and try this question yourself. Pause the video and try yourself, okay? Yes. So I hope you paused the video and you did this question yourself. Now, ma'am is going to solve this question. Let's see. We have a reaction A to 2B and C and all are your gases. Okay, ma'am. So A to you get 2B plus C. Initially, at T is equal to 0, you will have pressure P initial. You will not have anything here. At T is equal to some T time, you will have P initial minus X. This would be 2X and this would be X, right? Yes. And ma'am, P total would be the sum of all the pressures at T time. That is P initial minus X plus 2X plus X. So X cancel. So P total will be equal to P initial plus 2X. You can find the X value here. Yes, ma'am. X would be equal to P total minus P initial by 2. Clear, my dear students? Yes. Now we are supposed to write the rate expression, integrated rate law. K is equal to 2.303 by T log P initial by P initial minus X. So this would be equal to 2.303 by T log P initial by P initial minus what will be X. Let's see X expression. X would be P total minus P initial by 2. Yes, ma'am. So this will be P total minus P initial by 2. Let's solve this. This would be 2.303 by T log P initial 2 by 2P initial minus P total minus plus P initial. So from here you will get your expression K is equal to 2.303 by T log 2p initial by 3p initial minus p total. So this would be your final expression, right? Let's see which option is correct. 2p initial by 3p initial minus p total. 2p initial by 3p initial minus p total. Ma'am, option A is a correct answer. So if you were able to do this question yourself, then congratulations, your concept is clear, right? Yes, perfect. Let's move forward, my dear students. Next expression is your pseudo first order reaction. We've talked about first order reaction. What is pseudo first order reaction? My dear students, pseudo means something fake, someone who is lying, that would be pseudo, right? Yes. So now I am going to tell you how are you going to understand the pseudo first order reaction. Now you have to imagine that you have a reaction A plus B which is giving you some C, and I am saying you here that B is in excess, okay, and I'm also saying you that this is an elementary reaction. Ma'am is telling you it is an elementary reaction. If it is an elementary reaction, then ma'am, molecularity is equal to 2 and so is the order is also 2, right? No issues, perfect. Now my dear students, what I want to tell you is, imagine a ocean. If you talk about an ocean and you just take a bowl of water out of it, will it affect anyhow to the volume of the ocean? No, ma'am. Now you have a bucket full of water and you take out a mug full of water out of it. Yes, ma'am. Will it affect the volume of the bucket water? Yes, ma'am, it will affect. This means that anything, since we were talking about ocean was in a large amount. You just changed its volume by a mug or a bowl, it didn't affect it. But for the bucket, the same change actually affected. This is what I want to make you understand, that if something is in excess, that means it's a ocean. Now, if you will do some change to its concentration, the overall change would be very minimal, so that would be negligible. But if something is not in excess, then if you change their concentrations, they will have a major effect on their concentrations. So what can we say that, ma'am, since B is in excess, if you change its concentration, the overall change would be very negligible, so we can neglect it, okay? So my dear students, if we think about this particular reaction, we will say, ma'am, it is a second order reaction and the rate law would be written as R is equal to K A 1 B 1. But since B is in excess, it is in a large amount, its concentration will change, but that would be nearly constant. That is the reason that the new rate law would be K into B into A. Here, my dear students, this multiplication will give you a nearly constant value because change in concentration of B is very negligible because of its large amount present, right? Yes. So we can say that the new rate law would be some K dash into A, and now we see that it seems like it is a first order reaction. It seems like it is a first order reaction, and this is known as your pseudo first order reaction, which was actually a second order reaction, but since one of the reactant is in such a large amount that we consider it to be constant and it actually behaves like a first order reaction, right? We call it a pseudo first order reaction. I hope you got it. If you got it, now you will understand the points. Here are the points. The reaction is actually second order. It is actually second order, but looks like a first order reaction. This is called the pseudo first order reaction. If we let the reaction happen without any external changes, the rate is expected to decrease with decreasing concentration of A and B, but B is taken in excess and its concentration change is not showing up in the reaction because it is in large amount. Therefore, the rate is decreasing with the decreasing concentration of only A, and that is the reason it is considered to be a first order reaction, right? So what is a pseudo first order reaction? When you have two reactants and the amount of one reactant is so large that it is nearly constant, and the second order reaction actually behaves like a first order reaction. Perfect, very good. Let's move forward. Example would be acidic hydrolysis of ester. Acidic hydrolysis of ester, CH3C double bond O R plus H2O. Here, my dear students, water is in excess amount, you get CH3 C double bond OH plus ROH. Yes, perfect. Now, since water is in excess in such reactions, that is the reason this second order reaction also behaves like a first order reaction. So this is an example of pseudo first order reaction. I hope you get it. Perfect, my dear students. Now, next concept that we are going to talk about is, okay, with this we have completed our first order reaction, our zero order reaction, integrated rate laws, half lives, everything we've completed, right? We'll practice these questions at the end of the session as well. Now we are going to, till now the first thing that we discussed was that rate depends on, my dear students, concentration of reactant, and till now we were only discussing about the concentration of reactants, right? Now we are going on the second factor, which is your Arrhenius equation. Arrhenius equation, that is your temperature, how temperature affects the rate of a reaction. Okay, now when we talk about the rate of a reaction, we actually discuss, when we talk about the temperature of the reaction, we actually talk about the Arrhenius equation. What does Arrhenius equation tell? It describes the effect of temperature, the nature of reaction, and the catalyst on the rate constant of the reaction. It talks about the rate constant, which we were discussing till now, K. It tells us about this, right? Yes. So now let's discuss what is Arrhenius equation and how it defines the effect of temperature. Okay, so Arrhenius equation is applicable to elementary. So some few points which you need to remember about Arrhenius equation is that it is only and only applicable to elementary process, and that is one-step process. Here multi-process complex reactions are not involved, only and only one-step reactions, elementary reactions are involved. Since exponential term is unitless, okay, now I will have to tell you and then you will understand these points, right? Yes. So, Arrhenius equation. So, my dear students, Arrhenius equation has a particular expression which you just need to know. It's not where it came from or how it came from. It's out of your syllabus. You only have to know the expression, which is K is equal to A e raised to the power minus EA by R. T. Okay, this is your Arrhenius equation rate constant expression. What are the factors here? Let's say talk about these. K is your rate constant. A is your pre-exponential factor. It is your pre-exponential factor. My dear students, EA is the activation energy. I'll tell you about each and every term. Activation energy. R is your gas constant. And T is your temperature. And T is your temperature. Okay, perfect. Now let's talk about this expression. If you see, then your rate constant actually depends on temperature. If you see, my dear students, I can show you that as the temperature increases, you can see if your temperature is increasing, I'll show it by white color. White. If your temperature is increasing, then this overall value would decrease. I hope you understand this. So something in negative is decreasing. My dear students. So what can you say? You can say that your rate constant actually is increasing. The rate constant actually is increasing, right? Yes. So when your temperature increases, your rate constant also increases. So you can say that as your temperature increases, your rate constant increases. And you know that rate is equal to K A raised to the power N. So if K is increasing, then your rate of the reaction will also increase. I hope you understand this. Yes. So if K is increasing, that means rate is increasing. If your K rate constant decreases, your K also decreases, right? So we see that as the temperature increases, your rate constant value will also increase. So it depends on the temperature directly, right? Yes, perfect, very good. Now Once you understand the Arrhenius equation and all its factors, now we will talk about some other factors as well. Now you have to plot a graph. How are you going to plot a graph? If K is equal to A e raised to the power minus EA by RT, you have to take log, right? Yes, taking log, my dear students. What can we say? Log K, ln of K, taking ln. Natural log, ln of K would be equal to ln of A. ln of K would be equal to ln of A plus ln of e raised to the power minus EA by RT, right? Ln of E is equal to ln of K. This is equal to ln of A plus ln of e raised to the power, you can write it as plus minus EA by RT, right? Yes. So we can say that if we want to convert it into log base 10, so ln of x is equal to 2.303 log x, right? So you're going to use this expression. So multiply this by 2.303, log k would be equal to 2.303 log a minus EA by RT. Divide the complete reaction equation by 2.303. You will get log k is equal to log a minus EA by 2.303 RT. Okay, yes, let's write this expression there. Log k is equal to log a minus EA by 2.303 RT. Now you have to write the straight line equation, that is your maths equation. Y will be equal to C plus mx. Okay, now y will be equal to log k. C, which is your intercept, would be equal to log a. X would be equal to 1 upon t, and my dear students, slope, which is equal to m, is given by minus EA by 2.303 R. So if you are supposed to plot a graph, you would say that the graph would be between y, that is log k, and time temperature, that is 1 upon t. And ma'am, this will be a straight line but with a negative slope. So the plot would be something like this, my dear students. The intercept would be equal to log a and slope will be equal to minus EA by 2.303 R. Right? Yes. This is how you are going to plot a graph between the rate constant and temperature. And you can see very clearly that as your temperature is increasing, this complete value will decrease. Yes, ma'am. If this will decrease, then my dear students, log a minus some small value will eventually increase your K value. So as the temperature increases, your K increases. Okay, so we can say that the rate constant is directly proportional to the temperature. Clear? Yes. So this is how we understand the temperature dependence of rate constant, and this is given by the Arrhenius equation. Right? Very good, my dear students. Let's move forward. If we'll talk about this. If, my dear students, K is equal to the expression which we know, K is equal to A e raised to the power minus EA by RT. Now, my question to you is, what will happen at T tends to infinity? If you have infinite temperature, what is the maximum value of your rate constant? Ma'am, if T will tend to infinity, then K will be equal to A e raised to the power minus 0. Anything power 0, this whole will be 0. I hope you understand. T would be infinity, so this whole expression would be equal to 0. E raised to the power 0 will give you 1, so K will be equal to A. So the maximum value that you can get for the rate constant is your pre-exponential factor. Right? Yes. So this is how you are going to find out the maximum value that you can achieve for rate constant, that will be at infinite temperature, and that will be equal to your pre-exponential factor. Okay, so now let's read the points. The first point is Arrhenius equation is applicable to elementary process. Yes, since exponential term is unitless, the unit of k and a would be the same. Imagine k is equal to a e raised to the power minus ea by r t. Okay, now since it is e does not have any unit. So my dear students, I hope you understand this, that this particular part is unitless, because E does not have any unit, right? Yes. So the unit of these both will be equal. And that is the reason we said at infinite temperature, K will be equal to A, right? They will have the same unit as well. This expression is unitless. So you can say that unit of EA will be equal to unit of RT, right? What is the unit of R that you are going to use? Joule per Kelvin per mole, right? And temperature unit is Kelvin. Yes, ma'am. So Kelvin inverse Kelvin will be cancelled out. So Joule per mole. Joule per mole. So this will be the unit for your activation energy EA. So EA unit here used will be Joule per mole, right? Yes. So this is how you can find out that what is the unit of your activation energy that you are going to use. Perfect. I hope you are clear with this. Next expression, my dear students, when the temperature tends to infinity, K will be equal to A, and A is called the maximum rate constant. The plot of ln K versus 1 upon T provides both the Arrhenius parameters. Yes, I hope you understand this as well. Very good. Okay, we'll solve this question. Before this question, I want to tell you something else as well. Okay, now we've talked about Arrhenius equation, we've talked about everything. Now we will be talking about the yes, just a second. Okay, now we've talked about Arrhenius equation. Now we will be talking about the activation energy. We are talking about activation energy. So you should know what is activation energy. I hope you remember that when we did plot a graph between reactant and product, I just showed you that this was your transition state, right? Yes. So my dear students, every reaction has some activation energy, and the activation energy is the difference between the energy of the reactant and the transition state. This is your activation energy. Okay, every reaction will have some activation energy. There is no reaction which has zero activation energy. This is not possible. For example, if you are asked to do any work, any kind of work, you definitely ask for something, right? You will say, I need 10 rupees, I need 15 rupees. If your mother asks you to bring something, you will say that give me 5 rupees, I'll bring this thing, right? So the minimum amount that you are giving your mother so that you'll do that particular job is your activation energy. Below that amount, you'll not do any work. If you get that amount, you'll definitely do the work. If you'll get more amount than that, you'll do that work even faster. But if you are not given that amount, if you are given minimum amount than your supposed value, you'll not do the work. The same way, the reaction takes place. If you have that minimum threshold energy, then the reaction will be done. If the reactants cannot achieve that minimum amount of energy, then the reaction is not possible. And this is your activation energy, okay, which is given in Arrhenius parameter by joules per mole. I hope you got this point. Clear? Yes, very good. Let's move forward, my dear students. Now, here is a question which you are supposed to do. See, read the question and try yourself. Consider the reaction A to B graph between T half and initial concentration of the reactant is given. Hence, graph between minus dA by dt and time will be. So, first of all, from this expression, my dear students, you are supposed to find out that which order of the reaction is there. And then you can solve this question as well. Okay, so now, if I see that T half is a straight line passing through the origin with A, I can remember that half-life only and only depends on the initial concentration. It is not independent, and if T half was independent, it would have been first order reaction. If I talk about this, I can say that T half is directly proportional to this. Remember this expression, it is an important expression. I am telling you here, my dear students, that in general, T half is directly proportional to 1 raised to the power A n minus 1, where A is the initial concentration of reactant and n is the order of reaction. And this particular expression is not valid for first order reaction. This is not valid for first order reaction. Always remember this. Okay. Yes. Other all orders, this is applicable. So now what can you see? Ma'am, it cannot be first order reaction. No, because it is directly proportional. If I see zero order reaction, if n was 0, then T half would have been directly proportional to A and it would be a straight line, right? Yes. So this expression tells me that the reaction is a zero order reaction. If it is a zero order reaction, that means that my rate is equal to a constant value, right? Yes, my rate is equal to my constant value. It will not depend on any factor. It will not depend on the concentration of the reactant. It will be a constant value with time, right? Now, my dear students, minus dA by dt is actually giving you the rate. So you have to tell the rate with respect to time. Rate with respect to time for zero order reaction is a constant value. We just calculated. R is constant. Yes, ma'am. So rate will be a constant value. That is option C will be your correct answer. Option C would be your correct answer. So this is how questions are asked. You have to see the graph. You have to find the order of the reaction, and then eventually you can calculate the other orders as well. You can see the other graphs as well. Perfect. Yes. Let's move forward. Next question, my dear students. Here is the question and you have to solve this question. Actually, we've done this question, so I am giving you this question as your homework. You can take the screenshot here. The same type of question we have done in the class. So this is a homework question. Just take the screenshot. Okay. Now let's start. This is your homework question. Now we are going to move forward. Next question, next point, which is your collision frequency of. Now we are going to talk about the collision frequency. My dear students, I just gave you an expression that K is equal to A e raised to the power minus EA by RT. Here we know that reactants, for a reaction to get completed, they need that minimum amount of energy, that is your activation energy. So first condition for a reaction to happen is minimum activation energy, right? They need to have the minimum activation energy. What all factors do they need for a reaction to occur, right? We are talking about the pre-exponential factor A. My dear students, this pre-exponential factor A actually consists of Z and sigma. What is Z and sigma? Now we will be talking about this. Z is your frequency factor, which gives you number of collisions per unit time per unit volume. See, what does Z tell you? You know that if you have two reactants A and B and you want a product AB to be formed, so A and B need to collide with each other, only then your product will will be formed, right? Yes. So first condition is that you need that minimum activation energy. Yes. If the reactants have that minimum activation energy, then they must collide with each other. If they are colliding with each other, only then the product can be formed, right? Yes. So the second condition that you need for the reactants is that reactants should collide. Reactants should collide. Right? Yes. This is the second condition that is required for the reaction to be completed. First was minimum activation energy. Second was the reactant should collide, only then you will get a product, right? Will every time the reactants collide, they'll form a product? No. If they collide with the proper orientation, see, imagine A is here and B is here, right? And they do collide, but they just collide like this. You'll never get a product. You'll never get a good product. You will only get product when A and B collide in a particular orientation, that is AB. This is the particular orientation. If they will collide like this, only then you will get the product. This means that you need actually 3 conditions. What are the 3 conditions? Minimum activation energy. If the reactants have minimum activation energy, then they will collide. If they collide, then they should have the proper orientation of the collision, and only then your product will be formed, right? So my dear students, here EA gives you the minimum activation energy required. A consists of Z and sigma, where Z is the number of collisions per unit time per unit volume. How many collisions are taking place? That is given by Z. But sigma tells you the effective collisions. Effective collisions are the collisions where definitely the particular orientation is applied and you will get your product. So this is what collision frequency tells you. Collision frequency tells you the major 3 types. So the third condition would be proper orientation. Proper orientation. So for a reaction to happen, you need 3 major conditions. Minimum activation energy should be achieved. There should be collision and there should be effective collision. So minimum activation energy factor is given by EA. A consists of Z and sigma. Z stands for the number of collisions that are taking place. There will be a lot of collisions, but only the effective collisions are considered in the sigma part. Okay, so this is what is known as your collision frequency. The reactant molecules, collision theory of kinetics. The reactant molecules must collide for the reaction to take place. This is important, and the molecules must collide with the minimum energy known as your threshold energy, and that too with the proper orientation. So this is given by the collision theory of kinetics. I hope you got this point. Yes, very good. Let's move forward. The next factor that we are going to discuss is catalyst. Right? How catalyst affects the rate of a reaction. Now, how are you going to study this effect? I am going to give you an example again. Imagine you are here and there is a big mountain over here, and this is your destination. And this is your destination, right? Yes. So my dear students, if you are standing here and you want to go to your destination, you're very new here, you don't know the people around here, so you will see that you only have this path to go to your destination. That means it will take a lot of energy, it will take a lot of time for you to reach to your destination. See, so ma'am, I can say that this is my path 1. I can say this is my path 1. Yes. Now you have a second path as well. How do you have a second path? Imagine you are very lucky. Imagine you are very lucky and you get a person here who's generous person, who's good person. So what will he do? He is a commoner there. He actually lives there, so he knows all the ways there. You ask him that you need to go to this destination. What all are the possibilities that you have? He gives you a very small shortcut. He says that you can go from this path, which is your path 2. I know that this is a different path, but this is very easy path and you will reach very early. Right? Yes. So here, my dear students, this person is your catalyst. This person is your catalyst. What catalyst do? It just see, your initial and final positions were not affected. Your initial and final positions were not affected. Only the path in between was changed. So catalyst never initiates a reaction, and catalyst actually never ever changes the initial and final destinations. It only provides you a different path so that you can take, so that the reaction can be done over a more faster rate. And the second most important thing about catalyst is that catalyst actually participates in the reaction. This person actually went with him, right? But at the destination, he just left you and he just went away. That means catalyst, if you are using a catalyst in the initial amount, then after the reaction, you will get the same amount of catalyst back. This doesn't mean that the catalyst did not take part in the reaction. It did took part in the reaction, but it was recreated in the initial amount which you used it. Okay, so catalyst actually participates in a reaction also, but it regenerates itself in the product side. It does not appear in your product. Okay, you got this point as well. Next, my dear students, since thermodynamic parameters are actually the parameters which depend on the initial and final concentration states only, because they are state functions. Let us talk about delta G or delta H or delta U. All these thermodynamic parameters are state functions. I hope you remember thermodynamic state functions which depend on initial and final states. If the initial and final state is same, then will the catalyst affect these thermodynamic parameters? No, they will not affect the thermodynamic parameters. Okay, so these are the few points which you need to know about the catalyst. Let's see what all is given here. A catalyst can change the rate constant. It can change the rate constant and eventually it will change the rate. I will tell you how. Okay, so a catalyst can change the rate constant of a reaction at constant temperature. Next, if it increases the rate constant, it is called a positive catalyst. See, there will be a person who can make your journey easy. There can be a person who can make your journey difficult as well. So there are positive catalysts as well as negative catalysts. Okay, I'll tell you how they affect. If it decreases the rate constant, it is called a negative catalyst. If nothing is mentioned in the question, we assume a positive catalyst. Okay, catalyst does not change the initial or final state. Very important point, my dear students. Therefore, changes in the thermodynamic state functions, delta H, delta U, delta G, whatever, would be unaffected by the catalyst. Therefore, a catalyst cannot initiate a reaction. If a person does not want to go to the destination, if I am standing here and I don't want to go to my destination, a catalyst cannot take me to the destination. If I have that minimum amount of energy, if I have that activation energy, that I can perform that reaction, only then catalyst will help me. Otherwise, the catalyst cannot help me. So, a catalyst cannot at all initiate a reaction. If a reaction is possible, only then catalyst is effective. Okay, perfect. Very good. Let's move forward. Now, we are going to talk about different type of catalyst. Catalyst participates in the reaction but remains intact in the end of the solution. I told you, if you have some A and C catalyst you are using, then in between the reaction, that is your transition state, A will react with C. Okay, it will form some intermediate, but at the end you will get your product and C will be, your catalyst would be intact as the initial one. If here it was 1 molar, then at the end of the reaction also you will get catalyst as 1 molar amount. It will not be present in your product. Okay. Second point, last point, since catalyst appears as a product, it can be reused and a little of catalyst is good enough for the reaction. Now the question is how a positive catalyst increases the rate of a reaction, how a negative catalyst decreases the rate of a reaction. Okay, now we are going to talk about this positive catalyst. A positive catalyst provides an alternative path. It provides a different path to the same final product and it requires comparatively less activation energy. So basically, if you think about a reaction, let us say this is your energy, this is your reactant and product. Okay, so what will you say? You will say, ma'am, this is what? This is my activation energy, right? Yes. If I decrease your activation energy, if I somehow decrease your activation energy, obviously the reaction would be faster. Yes, ma'am. So what does the catalyst do? Catalyst actually decreases. Can I plot it with pink here? Catalyst actually decreases the activation energy. A positive catalyst decreases the activation energy. And you know that K is equal to A e raised to the power minus EA by RT. Now, if your activation energy is decreased, if activation energy is decreased, then your rate constant increases. If your activation energy is decreased, your rate constant increases, and if K increases, then rate of the reaction also increases, right? Yes. So what does a positive catalyst do? Ma'am, positive catalyst actually decreases the activation energy and eventually it increases the rate constant and eventually it increases the rate of the reaction, right? Yes, very good, perfect. Let's talk about the negative catalyst. What does the negative catalyst do? This is very important, and for your JEE and NEET, this is the most important thing. Does this also increases the activation energy? No, my dear students, it does not increase the activation energy. A negative catalyst actually, how does it decreases the rate? It decreases the rate by decreasing the pre-exponential factor, and eventually your K will decrease, that is your rate constant will decrease, and if your rate constant decreases, rate of the reaction will also decrease. So negative catalyst actually decreases your Arrhenius parameter, right? Yes, in presence of a negative catalyst, the pre-exponential factor decreases and the rate constant eventually decreases. It does not affect the activation energy, it decreases the pre-exponential factor, and eventually your rate constant will decrease and your rate of the reaction will also decrease. Perfect, very good. So now you have some questions, right? Yes, we've talked about all the factors till now, whatever that is in your syllabus of chemical kinetics. So now we will practice some questions, my dear students. I think we have completed, and now we are going to practice few questions, and then we'll round up the session. And radioactivity chapter would be discussed later in a different session. Okay, so don't worry, we will cover that topic as well. So now let's practice the questions. Okay, the first question is on your screens. How are you going to solve this question? Initial rate is given as Ka2 B1. By what fraction initial rate will change if initial concentration of A is taken 1.5 times and B is tripled? Okay, so if initial rate R is given by K A whole square B power 1, and then if you change the concentration, obviously your rate will change, and the concentration of A is increased by 1.5 times, so this would be 1.5 A whole square, and B is tripled, so this would be 3B power 1, right? Yes, 1.5 times whole square would be, I guess, 2.25. Yes ma'am, this would be 2.25 into 3 K R dash would be equal to A square, and this would be B1, right? So 3 5 15 5 1 3 to 6 7 3 to 6 6.75, and if you see this expression is actually R, so this would be R, so R dash, the new rate would be 6.75 times more than the initial rate. So option C would be your correct answer. Please check the calculations, please. Okay, yes, so I hope you will check the calculations, but according to me, option C is the correct answer. Let's move forward. Next question, my dear students. Next is, if you have a reaction A plus B gives you C, rate is Ka power half and B2. Initial concentration of A and B are increased by a factor of 4 and 2. Then initial rate is changed by a factor. So now, my dear students, this will be your homework. If we have done first question, then this will be your homework, because this question is exactly like that. Okay. So now you have to solve this question and you have to tell me in the comment section what is your answer. Perfect. Let's move forward. Next question. Which of the following represent the expression for 3/4 life of the first order reaction? Pause the video and do this question. Let's see what is the answer. If I talk about the rate expression, then T is equal to 2.303 by K log A naught by AT. Here, my dear students, AT will be equal to, ma'am, 3/4 life is done. 3/4 of your reactant is consumed. So A naught minus 3/4 of A naught. This will be 1/4 of A naught, right? Yes. So put it here. T is equal to 2.303 by K log A naught by A naught by 4. A naught cancelled. So T would be 2.303 by K log 4. Log 4, right? So 2.303 by K log 4, ma'am, option C would be a correct answer, right? Yes, this is how you are going to solve this question. Let's move forward. Next question, my dear students. For an elementary reaction, half-life period is 10 minutes. You are given half-life period as 10 minutes, and in what period of time would concentration of X be reduced to 10% of its original value? It is the elementary reaction, so you can say this is a first order reaction, right? Yes, ma'am, this is a first order reaction. If it is a first order reaction, you are given T half. You know that T half is equal to 0.693 by K. So you can find the value of K as 0.693 by T half. T half value is given as 10. So this would be 0.0693. right? Yes. In what period of time would concentration of X be reduced to 10% of original volume? Now, my dear students, it is saying that it is reduced to 10% of initial volume. This means that 10% of initial volume is actually left. It is not consumed. It is not telling you that 10% reaction is completed. No, it is saying that the concentration of X is reduced to 10%. This means that A of T is 10 upon 100 of A of T. It is reduced to 10% of original reaction. So A of T will be equal to 10 upon 100 of A naught. Okay, so 10% of the original concentration, it is reduced to 10%. So 10% of A naught is left. So this would be A naught by 10. Okay, so now it is very easy, ma'am. The expression would be K is equal to 2.303 by T log A naught upon A of T, which would be A naught by 10. A naught cancelled by A naught. K value you have 0.0693. Put it here. You can calculate the T value. You can calculate the T value. Okay. I hope you can do this question, my dear students. I'll put the value as well. The K value would be 0.0693. This will be equal to 2.303 upon T log 10. Now you have to solve this question and you will get your answer. Do let me know in the comment section what was your answer, right? Yes, I am giving you all these steps, calculations you have to do on your own. Okay, perfect. Let's move forward. Next question, my dear students. Next question is an elementary reaction between A and B is a second order reaction. Which of the following rate equations must be correct? An elementary reaction between A and B is a second order reaction. So you are given an overall order which is 2. Now you have to find which of the following is giving you an overall order of 2. But it is an elementary reaction. You should know that for elementary reaction, molecularity should be equal to order. And we know that molecularity cannot be fraction or negative value or zero value, right? Yes. So here if I see this is 2, this is 0. Okay. Can your molecularity be 0? No, ma'am, this cannot be possible. Fractions, not possible. 2 plus 0, again not possible. 1 plus 1, yes, ma'am, this is the whole value. So option D is your correct answer, right? Yes. So this is how you are going to calculate, because it was given a hint that elementary reaction is taking place. So you have to find out the order according to that question, right? Yes. So I hope you got the answer D. Perfect. Let's move forward. Next question. For a reaction, you are given an expression. You have to give the correct plot. Okay. So if you see here, then you can say that, what can you say? Ma'am, I know that K is equal to A e raised to the power minus EA by RT. Ln of K is equal to Ln of A minus EA by RT. Okay, you have to just convert it and you will get log K is equal to log A minus EA by 2.303 RT. Right? You are given this expression. Yes, ma'am. So here I can say that, okay, K, we have to just relate it to this. We were not supposed to do this. Okay, so I'll just erase it. Okay, ma'am. So my dear students, from here, I can say that this is something. Okay, wait. We are supposed to do this. This would be Y is equal to C plus M and X. Here, Y will be equal to log K. X would be equal to 1 upon T, right? And C would be equal to log A. And slope M would be equal to minus EA by 2.303 R, right? Yes. Now relate this expression with this. K value. Next is your A value. A is 1.2 into 10 raised to the power 14. So I can say that C will be equal to log 1.2 into 10 raised to the power 14. I just related it. Perfect. Next, my dear students, K is equal to A e raised to the power minus EA. So this value is for your EA upon R into t, right? So the first expression says that log k versus log t will be a straight line. Is log k versus log t a straight line? No, ma'am. Log k versus 1 upon t is a straight line. Okay, so log a versus 1 upon t is a straight line. So ma'am, this expression is not right. Log k versus log t will give a straight line. No, this will not give. Log 1 upon t, no. Log k versus 1 upon t, yes. So option D will be your correct answer. Option D would be your correct answer. Right? Yes. So log k versus 1 upon t will give a straight line. Option D would be my correct answer. So this is how you are going to solve these questions. Okay, let's move forward, my dear students. Next question and the last question of this session. Okay, let's see what does this question say. This question says that indicate the ease with which reaction takes place. You have 3 different reactions with 3 different activation energies, right? Reactant to product you are going. You have to tell which reaction will be faster. The one with which has lower activation energy will be faster. Yes, why? Because decrease in activation energy increases the rate constant and eventually it increases the rate of the reaction, right? So ma'am, the fastest rate would be for C, then would be for B, and then would be for A, right? Yes. So C, B, A, that is option B would be your correct answer, right? Yes. Very good, bache. With this, we have came to the end of this session. I hope you got all the points which I wanted to convey you, my dear students. I hope you practiced a lot, or I hope you understood every concept. Do let me know in the comment section how was this session for you, and you have to practice a lot of questions to gain confidence again in this particular chapter. Physical chemistry is all about practice. So I had a great time. Do let me know how was your experience. We'll meet in the next session, my dear students. Till then, keep studying. All the very best. Thank you so much.